stand in front of a mirror, strip down completely. Now really look at yourself. What you're seeing is one of the strangest bodies in the entire animal kingdom. Not because of how we're built or how we move, but because of what we're missing. Fur. We're apes. Members of the great ape family that includes chimpanzees, bonobos, gorillas, and orangutans. Every single one of our closest relatives is covered in thick protective hair from head to toe. Dark fur on chimpanzees, silver-backed coats on male gorillas, shaggy orange covering on orangutans. They look like what apes are supposed to look like. Then there's us, essentially naked, smooth-skinned, exposed. That's what your ancestors look like too. Not your great-great-grandparents. We're talking millions of years back, before humans were even recognizably human, before we built cities or invented writing or discovered fire, back when we were just another species of ape trying to survive in the forests of Africa. And somewhere along that incomprehensibly long journey, from then to now, we lost it. Almost all of it. The thick protective coat that every single one of our primate relatives still wears today. Think about that for a moment. Chimpanzees have fur, gorillas have fur, orangutans, bonobos, gibbons, every species of monkey you can name, they're all covered head to toe in protective hair. But us? We're essentially naked. Bizarre outliers in a family of furred creatures. The weird cousins who showed up to the evolutionary reunion without proper clothing. This isn't just a curiosity. This is one of the most important questions in human evolution. Because losing our fur didn't just change what we looked like, it changed everything. How we hunt, how we survive heat, how we communicate, how we think about clothing and shelter and fire, how we read emotions on each other's faces, even how our brains grew to their current enormous size. Every aspect of being human connects back to this one strange transformation. The moment our ancestors went from furred apes to naked apes, everything else became possible. If you're listening to this to fall asleep, perfect. That's exactly why I make these. So maybe subscribe and tell me where you are and what time it is right now. I check the comments and it's wild. Tokyo at 3 in the morning, London during a rainy afternoon, someone in Alaska at midnight, all of us wondering about the same profound mystery. Why did we lose something that seemed so essential? Because here's the thing that keeps evolutionary biologists awake at night. Fur isn't just decoration. Every mammal on Earth has it for very good reasons. It protects against sunburn, it provides insulation in the cold, it helps regulate temperature in both hot and cold environments, it offers a barrier against parasites and injuries, it plays crucial roles in social signaling and sexual attraction. Evolution doesn't just throw away useful adaptations on a whim. For natural selection to strip away millions of years of mammalian heritage, something significant had to happen. Some environmental pressure had to become so intense, so unrelenting, that being naked became more advantageous than keeping our fur. And scientists have been arguing about what that pressure was for over a century. Charles Darwin himself was puzzled by human hairlessness. The man who explained why giraffes have long necks and why birds have different beak shapes couldn't quite figure out why humans lost their fur. He eventually settled on an idea involving sexual selection. Basically that our ancestors found hairless partners more attractive. But even Darwin wasn't entirely convinced by his own explanation. Since then, researchers have proposed at least a dozen different theories. Some think we lost our fur because we started running long distances in the hot African sun and needed to cool down through sweating. Others believe it happened when our ancestors spent time in and around water, developing semi-aquatic lifestyles. Some scientists argue it was about parasites, that getting rid of fur meant getting rid of disease-carrying ticks and lice, and there are theories involving social signaling, thermoregulation, even brain development. Here's what makes this mystery so fascinating. They might all be partially right. Evolution doesn't usually happen for just one reason. It's messier than that. Multiple pressures working together, each one nudging our ancestors toward less and less body hair over millions of years. But the fact remains that something dramatic happened. Something that made our ancestors different from every other primate that ever existed. Out of over 5,000 mammal species on Earth, we're one of the very few that decided fur wasn't necessary anymore. We're in the same category as elephants, rhinoceroses, hippopotamuses, and whales. And there's a reason those animals are hairless. They're either massive and live in hot climates where their size helps them regulate temperature, or they live in water where fur becomes a liability. We're neither. We're medium-sized terrestrial mammals. We should be covered in fur like every other ape, but we're not. Think about what our loss of fur actually means in practical terms. A chimpanzee can sleep outside in moderate climates without much trouble. Their fur keeps them warm enough to survive most nights. Try that as a naked human in a temperate climate and you're looking at hypothermia by morning. A gorilla can trek through thorny undergrowth without a second thought. Their thick fur provides protection. You, with your exposed skin, would be torn up within minutes. Other primates can handle temperature swings of 30 or 40 degrees without much difficulty. Naked humans need shelter, fire, and clothing just to survive a typical spring day in most of Europe or Asia. So if being naked made us so vulnerable, how did we become the most successful large mammal on the planet? How did these hairless, fragile creatures not just survive but dominate every terrestrial ecosystem from the Arctic to the Sahara? The answer is that our nakedness forced us to become inventors, not just tool users. Lots of animals use tools, but systematic, creative, problem-solving inventors who could adapt to any environment through technology and culture, rather than waiting millions of years for biological evolution to do the work. Lose your fur coat, and you need a replacement. That necessity drove the invention of clothing. But clothing isn't like picking up a stick to probe for termites. You have to imagine the finished product before you start. You have to understand abstract concepts like cutting, joining, and fitting. You need to develop entirely new technologies for scraping hides, processing plant fibers, creating needles and thread. More importantly, you have to teach these skills to your children. Clothing manufacture became one of the first truly complex technologies that required generational knowledge transfer. A young chimpanzee can learn to use a termite stick by watching their mother a few times. Learning to make a fitted garment from animal hides requires years of instruction and practice. This created selection pressure for teaching ability and learning capacity. Individuals who were better at acquiring and transmitting complex skills had survival advantages. Their children were more likely to survive cold nights. Their groups were more likely to thrive in challenging environments. And it wasn't just clothing. Without fur to provide insulation, we needed fire. Mastering fire meant mastering one of nature's most dangerous forces. It meant developing the cognitive capacity to maintain and control something that could easily kill you. Without the protection fur provides from sun and rain and thorns, we needed shelter. Not just temporary sleeping spots, but constructed spaces that required cooperation and innovation to build. Each vulnerability that came from our nakedness forced us to develop new capabilities, new technologies, new social systems, new ways of understanding and manipulating the world around us. Our hairlessness didn't just change what we looked like, it changed what we were capable of becoming. It transformed us from just another African ape into something unprecedented. A species that could adapt to any environment not through evolution, but through innovation. A species that could colonize an entire planet, not by developing specialized biology for each habitat, but by developing the cognitive tools to create specialized solutions for each challenge. But we're getting ahead of ourselves. Before we can understand why we lost our fur, we need to understand what we lost. What did our furry ancestors actually look like? What did that coat of hair do for them? When did the transformation begin? Let's put this in perspective. Take a moment to really think about how unusual hairlessness is in the mammal world. Of the roughly 5,200 mammal species currently living on Earth, only a handful have lost most of their body hair. And when you look at that short list, a pattern emerges. Elephants, the largest land mammals on the planet. Their massive bodies generate so much metabolic heat that fur would be a liability. They lose heat through their enormous ears instead. Rhinoceroses and hippopotamuses, again, large-bodied animals living in hot climates. Their size gives them a low surface area to volume ratio, making heat dissipation challenging. Hairlessness helps. Whales, dolphins, porpoises, fully aquatic mammals where fur would create drag and lose insulating properties when wet. They've replaced hair with blubber. Walruses and seals, semi-aquatic, relying on blubber rather than fur for insulation in frigid waters. Naked mole rats. These bizarre creatures live underground in large colonies where communal body heat and confined spaces eliminate the need for individual insulation. Manatees and dugongs, slow-moving aquatic herbivores in warm tropical waters, that's essentially the list. Less than a dozen groups out of 5,000 species, and every single one of them has a clear environmental reason for their hairlessness. Size and heat in hot climates, aquatic lifestyle, underground colonial living. Now look at where humans fit. We're not particularly large. An adult human weighs maybe 150 to 200 pounds on average. That's small compared to elephants and rhinos. We're terrestrial, not aquatic like whales and seals. We don't live in underground burrows like naked mole rats. By every logical criterion, we should have fur, but we don't. And this apparent contradiction has puzzled scientists for over 150 years. What makes it even more puzzling is that our hairlessness isn't partial or limited to specific body regions like it is in some animals. Dogs, for instance, have less hair on their bellies than on their backs. Horses have varying hair density across different areas. But humans? We've gone almost completely naked over most of our body surface. Sure, we have those millions of hair follicles, but the vast majority produce only vellus hairs, those tiny, nearly invisible wisps that serve almost no function compared to the terminal hairs that cover other primates. It's like we kept the machinery for growing fur but turned it down to the lowest possible setting almost everywhere except our heads. The contrast with our closest relatives makes this even more striking. A chimpanzee has roughly the same number of hair follicles per square inch as a human, but their follicles produce thick, pigmented, visible hairs, terminal hairs that actually do something. Our follicles mostly produce nearly invisible fuzz. This tells us something important. Hair loss in humans wasn't about eliminating hair follicles entirely. It was about changing what type of hair those follicles produced. Somewhere in our evolutionary history, the genetic signals got modified. Instead of producing coarse, visible terminal hairs, most of our follicles switched to producing fine, nearly invisible vellus hairs. That's a specific, targeted genetic change. Not a random loss, a modification that required precise evolutionary pressure to select for. Which brings us back to the central question. What pressure? What environmental challenge was so intense that it drove this dramatic transformation? Because the story of human hairlessness isn't just about what happened. It's about what had to happen for everything else that makes us human to become possible. The clothing, the fire, the shelter, the complex social communication, the enormous brains, all of it traces back to those first ancestors who started losing their protective coat of hair under the African sun millions of years ago. The ones who discovered that being naked, despite all its apparent vulnerabilities, could be the greatest evolutionary advantage of all. If you were smart enough and social enough, and innovative enough to work around the problems it created. And here's what's truly remarkable. The transition wasn't instantaneous. It took millions of years, countless generations living, reproducing, dying, each generation slightly less hairy than the one before. The change so gradual that no individual would have noticed it in their lifetime. But over the vast expanse of evolutionary time, the transformation was total. Imagine standing at any point in that timeline, 3 million years ago, looking at a group of our ancestors. They probably looked like strange chimps, walking upright more often but still covered in protective fur. Jump forward to 2 million years ago. The fur is thinning, becoming less dense. The skin beneath is darkening, adapting to increased sun exposure. Fast forward to 1 million years ago. The transformation is nearly complete. Mostly bare skin, sweat glands proliferating, only strategic patches of hair remaining. Each of these snapshots would look dramatically different. Each represents a different stage in our journey from furred ape to naked ape. And yet the individuals living at each stage were just trying to survive, completely unaware they were part of an evolutionary revolution. So let's go back. Back to a time when our ancestors looked nothing like us. Back to the forests of Africa 6 million years ago when our lineage first split from chimpanzees. Back to when we were still completely, thoroughly, undeniably furry. Because that's where this story really begins. Not with the mystery of why we lost our fur, but with the reality of what that fur was, and why every other mammal on Earth decided it was worth keeping. The transformation from furred ape to naked ape took millions of years. It happened gradually, imperceptibly, generation after generation. No single individual woke up one morning suddenly hairless. But over those millions of years, the pressure mounted. The environment changed, new ways of living emerged, and slowly, inexorably, our ancestors shed the protective coat that had served mammals for hundreds of millions of years. What they gained in exchange would change the world. 6 million years ago, your ancestors didn't look anything like you. They were about 4 feet tall, walking upright more often than their chimpanzee cousins, but still spending plenty of time in the trees. And they were covered absolutely covered in thick, coarse hair, not the fine, almost invisible vellus hair that covers most of your body today. We're talking real fur, dense enough to see from a distance, thick enough to provide actual insulation, patterned enough that individuals probably had distinctive markings. This wasn't some kind of evolutionary mistake or primitive holdover. This was the standard primate operating system. Hair that covered every inch of skin except the palms, soles, and a few patches on the face. Hair that served dozens of critical functions that kept our ancestors alive in a world full of dangers we can barely imagine today. And we know they looked like this because of two types of evidence that paint an incredibly detailed picture of our hairy past. First, there's the genetic evidence. Every human alive today still carries the genes for full body hair. They're right there in your DNA, mostly switched off, but occasionally expressing themselves in ways that remind us of our furry heritage. Men with hairy backs and chests, women with hirsutism, excessive body hair, children born with hypertrichosis, a rare condition where they're covered in thick body hair from birth. These aren't genetic mistakes, they're evolutionary throwbacks, glimpses of what we all used to look like before something happened to switch off those hair-growing genes across most of our bodies. The genes responsible for hair growth are ancient, so ancient that we share most of them with mice, dogs, and every other mammal on the planet. The specific variants that regulate human hair growth patterns diverged from our chimpanzee cousins around 6 to 7 million years ago, and those early variants coded for full body coverage. We know this because when scientists compare the genetic sequences responsible for hair growth across primate species, humans stand out like a sore thumb. We have all the genes for thick body hair. We just have additional regulatory sequences that suppress their expression over most of our bodies. It's like having a fully functional car sitting in your garage with the emergency brake permanently engaged. All the parts work. They're just being held back by a few extra control mechanisms that evolved relatively recently in evolutionary terms. This tells us something crucial. Hair loss in humans wasn't about losing the genes for hair. It was about evolving new switches that turned those genes off in specific locations. The machinery is still there. It's just not being used the way it was for millions of years. The second line of evidence comes from comparative anatomy. Look at a chimpanzee, really look at one. Under that dark fur, their skin is pale, almost white in places. The hair isn't just decoration, it's protection from the sun, insulation against cold nights, a barrier against insects and parasites. Now look at human skin color distribution. The darkest skin pigmentation appears in populations that have lived near the equator for the longest time. Populations in sub-Saharan Africa, parts of South Asia, Melanesia. This is a clue, a big one. If our ancestors had kept their fur, they wouldn't have needed dark skin. The hair would have provided protection from ultraviolet radiation. The fact that populations developed dark skin after losing their hair tells us the hair loss came first and the pigmentation adaptation came later. But what exactly did that ancestral fur do for our early ancestors? Why was it so important that every primate species kept it for millions of years? Let's start with thermoregulation. Fur is one of nature's most sophisticated climate control systems. It works both ways, keeping heat in when it's cold, keeping heat out when it's hot. Those dense layers of hair trap air close to the skin, creating an insulating barrier that moderates temperature changes. On a cold night in the African forest, when temperatures could drop to 50 degrees Fahrenheit or lower, that fur would have been the difference between comfortable sleep and dangerous hypothermia. But it wasn't just about staying warm. In the heat of the day, properly maintained fur actually helps keep you cool. The hair creates a barrier between direct sunlight and the skin, preventing solar radiation from heating the body directly. Watch a lion or a wolf in the summer. They don't lose their coats. The fur shades their skin, allowing air circulation underneath while blocking the most intense heat. Our ancestors' fur would have worked the same way. As long as they stayed in forested environments with plenty of shade and limited their activity during the hottest parts of the day, fur was a net positive. It protected them without overheating them. Then there's physical protection. Primate fur isn't soft and fluffy like a rabbit's. It's coarse, sometimes wiry, dense enough to deflect thorns, prevent insect bites, cushion minor impacts. When you're moving through thick vegetation, climbing trees with rough bark, sitting on rough ground, that layer of hair prevents countless small injuries that could lead to infections. And in a world before antibiotics, before even basic first aid, infection was a death sentence. Anything that prevented wounds was selected for strongly by natural selection. Parasites were another major concern. This seems counterintuitive at first. We tend to think of fur as harbouring parasites, and it can. But well-maintained primate fur actually provides a first line of defence. The hair creates a physical barrier that makes it harder for ticks, mites, and other ectoparasites to reach the skin. Modern great apes spend hours every day grooming, picking through each other's fur to remove parasites and debris. This isn't just hygienic, it's social. Grooming bonds strengthen group cohesion, establish hierarchies, maintain alliances. For our furry ancestors, that coat of hair was the foundation of their entire social system. And speaking of social systems, fur provided crucial communication functions. Primate hair isn't uniform. It forms patterns, highlights, colour variations that help individuals recognise each other. It can be raised when an animal is angry or frightened, making them look larger and more threatening. It changes texture and appearance with age, providing visible signals about an individual's maturity and health status. Chimpanzees have distinctive facial hair patterns, lighter-coloured beards, expressive eyebrow regions. Gorillas develop silver backs as they mature, a clear signal of dominance and breeding status. Our ancestors almost certainly had similar markings, hair patterns that helped them navigate complex social hierarchies without constant conflict. So when did we start losing all this functional, socially important protective body hair? The honest answer is we don't know exactly. Hair doesn't fossilise. You can't dig up a 3-million-year-old skeleton and tell whether it was furry or naked. But we can make educated guesses based on indirect evidence. And those guesses point to a surprisingly recent timeline, at least in evolutionary terms. The earliest hominin species, creatures like Sahelanthropus and Aurorin, who lived 6 to 7 million years ago, were almost certainly fully furred. They lived in forests, moved like other apes, faced the same environmental challenges. No reason to lose the hair. Even Australopithecus species, who lived from about 4 to 2 million years ago, probably retained most of their body hair. They were spending more time on the ground, walking upright more consistently, but they were still relatively small-bodied, still living in mixed woodland and savanna environments where fur would have been advantageous. The shift probably began somewhere between 2 and 1.5 million years ago, with the emergence of the genus Homo. Early Homo species like Homo habilis and Homo erectus showed significant changes in body proportions. They were taller, more linear, with longer legs relative to their torsos. This is a body plan optimized for efficient walking and heat dissipation in open environments. And here's where things get interesting. When you commit to a tall, linear body plan adapted for hot, open environments, fur starts becoming a liability instead of an asset. The genetic evidence supports this timeline. Studies of the genes responsible for skin pigmentation suggest that dark skin evolved somewhere between 1.2 million and 1.8 million years ago. This matters because, as we mentioned earlier, dark skin only becomes necessary after you lose the protective hair. The ultraviolet radiation that pale skin under fur could safely handle becomes dangerous when that fur disappears. Natural selection would have strongly favoured darker pigmentation as soon as hair loss exposed the skin to direct sunlight. By the time Homo heidelbergensis appeared around 700,000 years ago, our ancestors were probably mostly hairless. Not completely. They almost certainly retained head hair, which protected the brain from overheating and sun damage. They kept eyebrows, which channel sweat away from the eyes. They maintained eyelashes, which protect against dust and debris. They likely had some body hair, particularly in areas associated with scent glands like the armpits and groin. But the dense primate standard body hair was gone. Our ancestors had become, by primate standards, bizarrely naked. And this transformation would change everything. Because losing our fur didn't just change how we looked, it changed how we hunted, how we regulated body temperature, how we dealt with parasites, how we signalled socially, even how we thought about clothing and shelter, those remnants we still carry, the hair on our heads, our eyebrows, our eyelashes, the variable patterns of body hair that differ between individuals and populations. These aren't random leftovers. Each patch of hair we retained serves a specific function. Head hair protects the brain, the body's most heat-sensitive organ, from both overheating and hypothermia. Eyebrows keep salt-laden sweat from running into our eyes during exertion. Eyelashes protect against airborne particles. The hair in our armpits and groin helps disperse pheromones, chemical signals that still play a role in human attraction and social bonding. We are, in essence, strategically hairless. We lost the fur where it would have prevented effective cooling, but kept it where it served crucial protective or signaling functions. This wasn't random. This was natural selection operating with surgical precision over hundreds of thousands of years. But this raises the obvious question. Why? Why would evolution strip away a system that had worked perfectly for millions of years? What environmental pressure could have been strong enough to override all those advantages that fur provided? What changed in our ancestors' lives that made hairlessness, with all its apparent vulnerabilities, actually advantageous? That's what we need to explore next. The theories about why we lost our fur, and I promise you, some of them are stranger than you might imagine. Now we come to the big question. When exactly did humans lose their fur? And more importantly, why? Because here's the thing about body hair. It's not just decoration. Every mammal on Earth has it for good reasons. It protects against sunburn, provides insulation, helps regulate temperature, and offers a barrier against parasites and injuries. Evolution doesn't just throw away useful adaptations on a whim. Something significant had to happen to make hairlessness more advantageous than keeping our fur. And for decades, the most popular explanation has been what scientists call the Savannah Hypothesis. The story goes like this. Between 6 and 7 million years ago, our ancestors were living comfortable lives in the forests of Africa. They were covered in thick body hair, just like modern chimpanzees and gorillas. They spent their days moving through trees, eating fruits, leaves, and whatever small animals they could catch. Life was good. Then the climate changed. This wasn't a sudden catastrophe. This was a slow, grinding transformation that took millions of years. Africa was getting drier, forests were shrinking, and in their place, vast grasslands were spreading across the continent. These weren't the tidy lawns you see in suburban neighborhoods. These were wild savannas, open territories where tall grasses waved in the hot wind, where scattered trees provided occasional shade, and where the temperature during midday could reach absolutely brutal levels. To understand what was happening, we need to grasp the scale of this climate transformation. Between 10 and 5 million years ago, the Earth was going through one of the most dramatic climate shifts in recent geological history. Global temperatures were dropping. Ice was forming at the poles for the first time in millions of years. Ocean circulation patterns were changing. In Africa, the effects were profound. The Congo rainforest, which had once extended across much of equatorial Africa, began to fragment. Dry seasons became longer. Rainfall patterns shifted. Areas that had been continuous forest broke up into a mosaic of woodland patches separated by expanding grasslands. This wasn't happening everywhere at once. The transition occurred in waves, varying by region and altitude. Some areas retained dense forest cover, others transformed completely into open savanna. But the overall trend was clear and inexorable. The age of forests was ending, the age of grasslands was beginning, and this created an ecological crisis for forest-dwelling apes. Food sources that had been abundant became scarce. Territory that had been continuous became fragmented. Competition for the remaining forest patches intensified. Fossil evidence from this period shows exactly what happened. Some ape populations stayed in the shrinking forests, adapting to the changing conditions but remaining fundamentally forest creatures. Their descendants became modern chimpanzees, bonobos, and gorillas. Successful, certainly, but confined to specific forest habitats in Central and Western Africa. Other populations made a different choice. They moved out into the transitional zones, the woodland savanna mosaics where trees were scattered rather than continuous. These were our ancestors, and this choice set them on a path that would eventually lead to humans. The fossil record from this critical period is frustratingly incomplete. We have tantalizing fragments, a jawbone here, a few teeth there, occasionally, if we're incredibly lucky, a partial skeleton. But the complete picture of how and when our ancestors transitioned from forest to savanna remains unclear. What we do know is that by about 4 million years ago, creatures like Australopithecus afarensis, the species that includes the famous Lucy skeleton, were spending significant time in open environments. The chemistry of their fossilized teeth, which preserves signatures of the plants they ate, shows a diet that included more grasses and savanna plants than pure forest species would consume. Their skeletons show adaptations for bipedal walking. Not perfect bipedalism like modern humans, but definitely moving upright more consistently than chimps or gorillas. This makes sense for savanna living. Standing upright lets you see over tall grass. It reduces the body surface area exposed to direct overhead sun. It frees your hands to carry things, food, tools, infants, over long distances. But here's the critical detail. These early bipedal apes were still relatively small. Lucy stood about 3.5 feet tall. She probably weighed around 60 to 70 pounds. That's tiny compared to modern humans. And small body size actually made fur more viable. When you're small, you have a high surface area to volume ratio, which means you lose heat quickly. Fur can help prevent heat loss at night without causing too much overheating during the day, as long as you're not engaging in sustained high-energy activity. Our ancestors had a choice. They could retreat with the forests, staying in the shrinking woodland patches and competing ever more desperately for limited resources. Or they could adapt to the new environment, learning to survive in the open grasslands where no tree-dwelling ape had gone before. Some populations chose the first option. They stayed in the forests and eventually became modern chimpanzees and bonobos. But one lineage, our lineage, took the risk. They moved out into the open. And this decision changed everything. The savanna wasn't like the forest. In the trees, you could move from one shady spot to another, rarely exposing yourself to direct sunlight for long periods. But out on the grasslands, there was nowhere to hide from the sun. If you wanted to find food, you had to walk for miles under brutal heat. If you wanted to hunt, you had to chase prey across open ground with no shade breaks. And here's where the problem with fur becomes obvious. Body hair is great insulation when you need to. Stay warm. But when you're exercising in 100-degree heat, it becomes a death trap. Fur traps heat close to your body, preventing it from dissipating into the air. Modern chimpanzees deal with this by avoiding midday activity. They rest in the shade during the hottest hours, only moving around during cooler morning and evening periods. But our ancestors couldn't afford that luxury, because around the same time they were moving into the savannas, they were developing something revolutionary: bipedalism, walking upright on 2 legs. This adaptation is usually explained in terms of efficiency. Walking on 2 legs uses less energy than knuckle walking on all 4s, letting you cover more ground with less effort. But bipedalism had another crucial advantage that's often overlooked. It reduced sun exposure. When a chimpanzee walks on all 4s, its entire back is exposed to direct overhead sunlight. That's a huge surface area absorbing solar radiation. But when you stand upright, only your head and shoulders get hit by the midday sun. Everything else is shielded by your own body. This reduces heat load by about 60%. That's enormous. But even with reduced sun exposure, the savanna was still brutally hot. And this is where hairlessness enters the picture. Our ancestors needed a better cooling system, and nature had already provided the solution: sweating. Now, lots of animals sweat, but most mammals only have sweat glands in limited locations, like their paws. And the sweat glands they do have are called apocrine glands, which produce thick, oily sweat that's great for scent communication, but pretty useless for cooling. Humans are different. We're covered in eccrine sweat glands, millions of them, distributed across our entire body. These glands produce thin, watery sweat that evaporates quickly, carrying heat away from the skin with incredible efficiency. It's one of the most effective cooling systems in the animal kingdom. But here's the crucial detail. Eccrine sweat glands only work efficiently on bare skin. If you're covered in thick fur, the sweat gets trapped in the hair where it just sits there, being useless, instead of evaporating and cooling you down. So the hypothesis goes like this. As our ancestors adapted to savanna life and developed bipedalism, natural selection began favouring individuals with less body hair and more eccrine sweat glands. These individuals could stay active during the hottest parts of the day. They could walk farther to find food. They could hunt more effectively. Most importantly, they could practice what anthropologists call persistence hunting. This was the game changer, the hunting strategy that might have driven human evolution more than any other factor. Here's how it worked. You pick out a target animal, usually something like an antelope or a kudu, then you just start jogging after it. Not sprinting, just a steady jog. The animal bolts, running at full speed until it's far ahead of you. But you keep jogging. Eventually you catch up again. The animal runs away again. You keep jogging. Over and over for hours, sometimes for an entire day. The animal is faster than you in short bursts, but it can't sweat effectively. It can only cool down by panting, which means it has to stop running to catch its breath. Meanwhile, you're cooling down continuously through evaporative sweating. You never have to stop. You can jog for hours without overheating. Eventually, the animal simply collapses from heat exhaustion. Its internal temperature rises to dangerous levels. Its muscles stop working properly, and you walk up and kill it with a spear or a rock. It sounds brutal, because it is, but it's also remarkably effective. Modern hunter-gatherers in the Kalahari Desert still practice persistence hunting, and they can bring down animals that would be impossible to catch any other way. And this hunting strategy only works if you're hairless and covered in eccrine sweat glands. With fur, you'd overheat and collapse long before your prey did. Without fur, you become the most dangerous long-distance predator on the planet. The paleoclimate evidence supports this scenario. Between 3 and 4 million years ago, we see a dramatic expansion of grasslands across East Africa. This matches perfectly with the fossil record showing our ancestors developing bipedalism and leaving the forests. By 2 million years ago, we have early Homo species that show clear adaptations for long-distance running. Changed leg proportions, modified foot architecture, enlarged buttock muscles for stabilizing the trunk during running. These are the bodies of persistence hunters, and they would have needed hairlessness to make the strategy work. But there's more to the story. Hairlessness wasn't just about hunting. It was about surviving in a completely new environment where the old rules didn't apply. In the forest, overheating was rarely a problem, but dehydration was a constant threat because water sources were scattered and unreliable. Our savanna-adapted ancestors needed to travel long distances between waterholes, often carrying food or tools with them. This meant hours of walking in direct sunlight. Without an efficient cooling system, this would have been impossible. With hairlessness and eccrine sweating, it became routine. The genetic evidence adds another piece to the puzzle. Studies of skin pigmentation genes suggest that humans developed dark skin around 1.2 million years ago, right around the time we were losing most of our body hair. This makes perfect sense. Body hair protects against ultraviolet radiation. Once you lose that protection, you need something else to prevent skin damage and skin cancer. Dark skin, loaded with melanin pigment that absorbs and scatters UV rays, provided that protection. So the sequence probably went like this: savanna adaptation, then bipedalism, then gradual hair loss combined with increased sweating capacity, then darker, skin pigmentation to protect newly exposed skin from sun damage. Each adaptation building on the previous ones, creating a complete package optimized for surviving in open, hot environments. But as compelling as the Savannah Hypothesis sounds, it's not without problems. The biggest criticism is that the timeline doesn't quite match up. We know our ancestors were bipedal by about 4 million years ago, but the most dramatic reduction in body hair probably didn't happen until much later, maybe 1 to 2 million years ago. That's a huge gap. If hairlessness was immediately advantageous for bipedal savanna living, why did it take millions of years to evolve? Some researchers suggest the early bipedal hominins might have retained their fur because they were still living partially in woodland environments, only moving into fully open savannas much later. Others think hairlessness might have evolved in stages, with different body regions losing hair at different times and for different reasons. Another problem is that not all populations living in hot, open environments are hairless. Aboriginal Australians lived in conditions very similar to the African savanna for tens of thousands of years, but they retained normal human body hair patterns. They didn't evolve to become more hairy just because the Savannah Hypothesis suggests hairlessness is optimal for those environments. This suggests that once hairlessness evolved, it became fixed in human populations regardless of local climate conditions, which means maybe it wasn't purely about savanna adaptation after all. Then there's the question of persistence hunting itself. While it's true that some modern hunter-gatherers practice this technique, it's far from universal. Many successful hunting societies have never used persistence hunting at all, so maybe it wasn't as important to human evolution as the hypothesis suggests. Maybe hairlessness evolved for different reasons, and persistence hunting was just a useful side benefit that some populations figured out how to exploit. Despite these criticisms, the Savannah Hypothesis remains the most widely accepted explanation for human hairlessness. It connects multiple lines of evidence into a coherent narrative. Climate change driving habitat change favouring bipedalism. Bipedalism creating thermal challenges selecting for hairlessness and improved sweating. Each step follows logically from the previous one, and the end result, hairless, sweating, long-distance running humans, matches exactly what we see in the fossil and genetic records. But science is never about finding one perfect explanation and calling it done. It's about testing hypotheses, identifying problems, and refining our understanding. The Savannah Hypothesis might explain much of human hairlessness, but it probably isn't the whole story. Other factors, other selective pressures, other evolutionary forces were almost certainly involved, and that's what makes this mystery so fascinating. We're not just asking why humans lost their fur, we're asking what it means to be human. How did we become this strange, hairless, sweating species that can run for hours under the blazing sun? What combination of environmental pressures and random mutations and selective advantages created something so unique in the mammalian world? The Savannah Hypothesis gives us part of the answer, but only part. The full story is more complex, more nuanced, and far more interesting than any single explanation can capture. Let's talk about something that most people never think about, something so mundane, so ordinary, that it seems barely worth mentioning: the fact that you can run. Not sprint, anyone can sprint for a few seconds, but actually run, cover miles and miles at a steady pace without stopping. This ability, this capacity for endurance running, is one of the strangest things about being human, because almost no other mammals can do it. Cheetahs are faster than us, sure, but they can only maintain top speed for about 30 seconds before they overheat. Horses can run for longer, but they still need to stop and rest regularly. Even dogs, those tireless companions who seem like they could run forever, will eventually collapse from exhaustion if you push them too hard in hot weather. But humans? We can just keep going. Hour after hour, mile after mile, in conditions that would kill most other animals. We're not the fastest runners on the planet, not even close, but we might be the best endurance runners ever to evolve, and this strange ability connects directly to our hairlessness. Because the two evolved together, reinforcing each other, creating a feedback loop that transformed our ancestors into the most dangerous pursuit predators the world had ever seen. Think about what running actually does to your body. Every muscle contraction generates heat. Your heart pumps faster, working harder, producing more thermal energy. Your metabolism ramps up, burning fuel, creating heat as a byproduct. All of this heat has to go somewhere. If it stays trapped in your body, your core temperature rises. Too high, and proteins start to denature. Organs begin to fail. Your brain, the most heat-sensitive organ in your body, starts to cook inside your skull. For most mammals, this is a hard limit on endurance activity. They can sprint, but they can't sustain it. They have to stop, seek shade, pant desperately to bring their body temperature back down. The faster they run, the more heat they generate, and the sooner they have to stop. Humans broke this limit. We found a way to run continuously without overheating, and that way was hairlessness combined with an unprecedented number of sweat glands. The numbers are actually staggering. Humans have between 2 and 4 million eccrine sweat glands distributed across our bodies. That's roughly 300 to 500 glands per square inch of skin, depending on the body region. Your forehead alone has about 200 sweat glands per square centimetre. Chimpanzees, our closest living relatives, have maybe 1/10 as many eccrine glands. They can sweat, but not nearly as effectively as we can, and most other mammals barely sweat at all. They rely primarily on panting to dump excess heat. But here's the critical insight. Panting doesn't work when you're running. You can't pant and gallop at the same time. The mechanics of breathing while running require a different pattern. So if you're a furred, four-legged mammal, you face an impossible choice. Run fast and overheat, or slow down and cool off. Humans don't face that choice. We can breathe however we want while running, and more importantly, we can sweat continuously while moving. Every drop of sweat that evaporates from our skin removes about 580 calories of thermal energy. Not food calories, thermal calories, but still, it's an enormous cooling effect. For this system to work, the sweat has to reach bare skin and evaporate into the surrounding air. Fur creates a microclimate next to your skin, a layer of trapped air that's warm, humid, and relatively still. Sweat that evaporates into this microclimate doesn't cool you efficiently. It just sits there, raising the humidity in your fur layer until evaporation slows to a crawl. You end up soaking wet and still overheating. Remove the fur, though, and everything changes. Sweat reaches bare skin. Airflow across that skin carries away the evaporated moisture immediately. The cooling effect is dramatic and continuous. This is what enabled persistence hunting. And recent research suggests this hunting strategy was far more widespread than scientists previously thought. For decades, skeptics argued that persistence hunting was too rare, too difficult, too energetically expensive to have played a significant role in human evolution. But a major study published in 2024 examined hundreds of historical reports from around the world. They found 391 documented cases of endurance pursuit hunting from cultures on every continent. Among 141 Western North American societies surveyed, 114, or 81%, practiced some form of persistence hunting. It wasn't just happening in the Kalahari Desert. It was happening in dense woodlands, on mountain slopes, across snow-covered terrain. Anywhere humans lived, they were using their unique running abilities to hunt. The mechanics are elegant in their simplicity. You select a target animal, something large enough to be worth the effort, a kudu, an antelope, a deer, then you start running toward it at a pace you can maintain. Not your maximum speed, just a comfortable jog that you could keep up for hours. The animal sees you coming and bolts. It's much faster than you in a sprint, so it quickly disappears from view. But you don't stop. You follow the tracks. You know the animal's behavior patterns. You know it will run until it feels safe, then stop to rest in whatever shade it can find. Your job is to not let it rest. You track the animal to its resting spot, then you appear again. The animal panics and runs. You keep jogging. The cycle repeats. The animal runs, rests. But each time it gets a little more tired, a little more overheated, a little less able to cool down during the rest periods. Meanwhile, you maintain the same steady pace. Your eccrine sweat glands are pumping out moisture. Your bare skin is evaporating it efficiently. Your body temperature stays stable. You're not getting tired, at least not significantly. You could keep this up all day. And eventually, after 4 hours or 6 hours or sometimes 12 hours of relentless pursuit, the animal collapses. Its cooling system has failed. Its body temperature has climbed into the danger zone. It literally cannot run anymore. You walk up and you kill it. Modern persistence hunters in the Kalahari have been documented bringing down kudus in as little as 2 hours during the hottest part of the day. The longest documented hunt took just over 6 hours. In every case, the key factor was human thermoregulation, the ability to keep cool while running in conditions that cause the prey animals to overheat. The anatomical evidence supports this. Around 2 million years ago, right when we see the most dramatic changes in body proportions and hair loss, we also see skeletal features that are specifically adapted for endurance running. Long legs with a high hip-to-knee ratio. This increases stride length and reduces the energetic cost of running. Modern humans have proportionally longer legs than any other primate. When you look at a human skeleton next to a chimp skeleton, the difference is striking. Our legs are like stilts compared to the relatively short lower limbs of our ape cousins. Shortened toes. Longer toes are good for grasping branches but bad for running efficiency. Our ancestors developed shorter, more robust toes, better suited for propelling the body forward with each stride. If you've ever noticed how short and stubby human toes are compared to chimp toes, which are almost like fingers, you're seeing this adaptation in action. An enlarged gluteus maximus, the large muscle in your buttocks. This muscle does very little during walking, but becomes extremely active during running. It stabilizes your trunk, preventing your upper body from pitching forward with each stride. Chimpanzees have relatively small gluteus maximus muscles because they don't run much. Humans have huge ones because our ancestors ran constantly. A nuchal ligament, an elastic structure in the neck that helps stabilize the head during running. Other primates don't have this. We evolved it specifically for running. When you run, your head wants to bob up and down with each stride. The nuchal ligament acts like a shock absorber, keeping your head stable and reducing the energy cost of maintaining balance. Long Achilles tendons that act like springs, storing and releasing energy with each stride. This elastic energy return reduces the metabolic cost of running by up to 35% compared to running without it. It's like having springs in your legs that give you back some of the energy you put into each step. Specialized foot architecture. Humans have a longitudinal arch in the foot that acts as a spring during running. When you land on your foot, the arch compresses, storing energy. When you push off, it releases that energy, helping propel you forward. It's an incredibly sophisticated piece of biomechanical engineering. the ability to decouple breathing from stride frequency. Most quadrupedal mammals have to synchronize their breathing with their gait. They take 1 breath per stride cycle. This limits their endurance because they can't adjust their breathing rate independently of their running speed. Humans can breathe however we want while running, taking multiple breaths per stride or 1 breath across multiple strides depending on our needs. All of these features appear in the fossil record around the same time hairlessness is emerging. They're not adaptations for walking. Walking doesn't require most of these features. They're adaptations for running, for sustained long-distance endurance running in hot environments. Let's look more closely at what modern persistence hunting actually entails, because the details are fascinating and reveal just how finely tuned the human body is for this activity. In documented hunts from the Kalahari, hunters begin in the hottest part of the day, often when temperatures exceed 100 degrees Fahrenheit. They drink as much water as they can hold, sometimes several liters, because they know they'll be sweating profusely for hours. They select a target animal, usually a kudu or similar antelope. The choice is strategic. The animal needs to be large enough to provide substantial meat, but not so large that it's dangerous when cornered. It needs to be in good enough condition to run, because a sick or injured animal won't run as predictably. The hunt begins with a steady jog toward the animal. The hunters don't try to be stealthy. They want the animal to see them and run. The kudu bolts, reaching speeds of up to 40 miles per hour. Within seconds, it's disappeared over the horizon, but the hunters don't sprint after it. They maintain their steady jog, maybe 8 to 10 miles per hour, a pace they can sustain for hours. They follow the tracks, reading the subtle signs in the disturbed soil and vegetation. A broken blade of grass here, a scuff mark there, hoof prints that tell them the animal's direction and how long ago it passed. After 15 or 20 minutes of jogging, they catch up to the kudu. It's resting in whatever shade it could find, panting desperately, trying to cool down. When the hunters appear, it panics and runs again. The cycle repeats. Each time, the kudu runs a little slower, rests a little longer, shows more obvious signs of heat stress, stumbling, excessive drooling, glassy eyes. Meanwhile, the hunters maintain exactly the same pace they started with. Their bodies are producing enormous amounts of sweat, sometimes over a litre per hour. But that sweat is evaporating immediately from their bare skin, keeping their core temperature stable. They're reading the animal's behaviour, making predictions about where it will run next, coordinating with each other if it's a group hunt, making strategic decisions about when to push harder and when to back off slightly. After 4 to 6 hours, sometimes longer, the kudu collapses. Its body temperature has climbed to dangerous levels, often above 107 degrees Fahrenheit. Its muscles are failing. It literally cannot run anymore. The hunters approach carefully. Even in heat exhaustion, a kudu can still kick dangerously. They dispatch it quickly, usually with a spear thrust. Then they begin the process of butchering and carrying the meat back to their group. The energetic calculations are revealing. A successful persistence hunt provides hundreds of pounds of meat. That's thousands of calories of high-quality protein and fat. The hunters might have expended 2,000 calories during the pursuit, but they've gained 20,000 or more in food value. From a pure energy economics perspective, it's incredibly efficient when it works. And the success rate, while not perfect, is surprisingly high in documented hunts. Studies show success rates of 50 to 70% for experienced hunters in suitable conditions. That's better than many other hunting techniques that require more complex technology or more dangerous close encounters with large animals. But persistence hunting wasn't just about the physical act of running. It required sophisticated cognitive abilities, tracking skills developed over years of practice, the ability to read subtle signs in disturbed vegetation, in animal behavior, in the patterns of the landscape. You had to understand your prey's psychology, predict where it would go, anticipate its behavior. You needed to understand the environment well enough to know where water sources were located, because you'd be sweating out liters of fluid during the hunt. You had to be able to navigate across featureless grasslands and find your way back to your group. And often, persistence hunting was a cooperative activity. Multiple hunters working together, taking turns pushing the prey, sharing knowledge about the animal's location and condition. This required communication, coordination, social bonds strong enough to sustain hours of cooperative effort. All of these cognitive and social requirements created selection pressure for increased intelligence. The hairless, sweating, running apes weren't just physically different from their ancestors, they were becoming smarter, more socially sophisticated, more capable of complex planning and cooperation. Recent analyses have shown that when persistence hunting is successful, it provides better caloric returns relative to time invested than many other hunting strategies. A hunter pursuing a gemsbok at a trot might drive it to exhaustion in 24 minutes, getting 5 times more calories per unit of time invested compared to slower stalking approaches. The energy cost of running is higher than walking, but the payoff when you succeed is substantial, and you don't have to succeed every time, even a moderate success rate, maybe one successful hunt in every 3 or 4 attempts, provides enough nutritional benefit to make the strategy worthwhile. Critics of the persistence hunting hypothesis point out that the technique is still relatively rare among modern hunter-gatherers. Many successful foraging societies have never practiced it, but this doesn't necessarily mean it wasn't important in our evolutionary past. Modern hunter-gatherers have access to technologies and strategies that our ancestors 2 million years ago didn't have. Sophisticated projectile weapons that allow killing from a distance, traps and snares, carefully planned ambush sites. These techniques might be more efficient than persistence hunting in many contexts. But 2 million years ago, before complex projectile weapons, before elaborate trapping techniques, persistence hunting might have been one of the most reliable ways to acquire large game. The anatomical adaptations we see in early Homo strongly suggest that running, specifically endurance running, was critically important to their survival. And those adaptations only make sense in the context of hairlessness. Try to imagine persistence hunting with fur. The sweat would soak into your hair, creating a heavy wet mass that clings to your skin without evaporating effectively. You'd be carrying extra weight in the form of waterlogged fur. Your body temperature would climb. Within an hour or 2, you'd be in heat stress. The prey animal would outlast you, not the other way around. Hairlessness didn't just enable persistence hunting, it enabled a whole suite of behavioral and ecological changes. It allowed our ancestors to be active during the hottest parts of the day, when other predators were resting. It let them travel long distances across open landscapes without succumbing to heat stress. It permitted exploration of new territories, expansion into diverse environments. And perhaps most importantly, it created the conditions for our large, energetically expensive brains to evolve. Because here's something most people don't realize. Your brain generates about 15 watts of thermal energy continuously, just from thinking and processing information and maintaining consciousness. That doesn't sound like much until you realize it's equivalent to having a small light bulb burning inside your skull 24 hours a day. For most mammals, this level of brain metabolism would create dangerous overheating during sustained activity. But humans, with our efficient whole-body cooling system, can maintain stable core temperatures even during intense physical exertion. This meant the brain never experienced the dangerous temperature spikes that would occur in furred animals during similar activity. The brain could grow larger, consume more energy, generate more heat. Because the body's cooling system, the hairless skin covered in sweat glands, could handle it. Some researchers think this created a positive feedback loop. Better body cooling allowed larger brains. Larger brains enabled more sophisticated hunting techniques and tool use. More sophisticated hunting provided better nutrition. Better nutrition supported even larger brains, and so on, spiraling upward toward the massive brains that characterize modern humans. The running revolution wasn't just about hunting. It was about becoming a different kind of creature, one that could outthink and outlast almost any prey, one that could adapt to new challenges through intelligence rather than just physical prowess, one that could cooperate in complex ways to achieve goals that would be impossible alone. And it all started with losing our fur and learning to sweat. Right now, as you're listening to this, your body is performing a feat of biological engineering that almost no other mammal on Earth can match. Millions of microscopic glands are monitoring your body temperature, ready to spring into action at the slightest hint of overheating. And if you're doing anything more strenuous than lying perfectly still in a climate-controlled room, they're already working, sweating. It sounds simple, maybe even a bit gross. But the human sweating system is genuinely extraordinary, one of the most sophisticated cooling mechanisms ever evolved by any terrestrial animal. And it only works because you're naked. Let me explain why this matters so much. Every mammal faces the same fundamental problem. Bodies generate heat, Muscles working, hearts pumping, brains thinking, all of this produces thermal energy that has to go somewhere. For most mammals, this isn't a huge deal most of the time. They can pant, they can seek shade, they can reduce activity during the hottest parts of the day. But for the human ancestors spreading across Africa during and after the Great Climate Shift, the heat problem was becoming critical. Because they weren't just surviving anymore. They were walking, endlessly walking, tracking game animals searching for water, moving between seasonal food sources, and they were doing it under the African sun in the middle of the day, when every other predator had the good sense to rest in whatever shade they could find. This created a metabolic crisis. Walking generates about 4 times as much heat as resting. Walking under direct sunlight adds the entire radiant heat load of the sun, potentially another 1,000 watts of energy per square meter hitting your body. Walking in pursuit of game that can run faster than you means maintaining this activity level for hours, maybe all day. Do that in a fur coat and you die. Not might die, will die. Hypothermia, heat stroke, organ failure. Your brain cooks inside your skull before you catch anything worth eating. Evolution had a choice to make. Either humans stay hairy and accept the limitations that come with it, restricted activity periods, shorter pursuit distances, less ambitious hunting strategies, or humans lose the hair and develop something better. They develop something better. And that something better is written across every square inch of your skin right now. You are covered, absolutely covered, in eccrine sweat glands. Between 2 and 4 million of them, depending on various factors like your ancestry, sex and age. That's somewhere between 300 and 5,000 glands per square inch of skin, varying by body region. Your forehead alone has about 200 sweat glands per square centimetre. That's over 1,200 glands per square inch, all dedicated to producing the thin, watery sweat that evaporates quickly and carries heat away from your skin. These aren't the same as the sweat glands in your armpits that produce the thicker, more odorous apocrine sweat. Those are different, older in evolutionary terms, more common across mammals. The eccrine glands that cover your body are special, unique to primates, and vastly more developed in humans than in any of our relatives. Chimpanzees have eccrine glands, but their density is roughly 10 times lower than ours, maybe 200,000 total across their entire body, compared to our 2 to 4 million. They can sweat, but not nearly as effectively as we can. And here's the really clever part. These glands don't just produce water, they produce a carefully calibrated mixture of water, salt, and other dissolved substances that's been optimized by millions of years of evolution for maximum evaporative cooling efficiency. When this sweat reaches your skin surface and evaporates, it removes heat. A lot of heat. Every gram of water that evaporates from your skin removes about 580 calories of thermal energy. That's not food calories, that's thermal calories, the physics unit of heat energy. But it's still an enormous cooling effect. A human engaged in moderate activity in a hot environment can lose 2 to 3 litres of water per hour through sweating. That's 2 to 3 kilograms of water, and when that water evaporates, it carries away between 1 million and 1,700,000 calories of heat energy per hour. For context, that's enough cooling capacity to offset the heat generated by running a marathon in hot conditions. It's why humans can run marathons at all, why we can chase prey animals to exhaustion, why we can be active during the hottest parts of the day when other large mammals are resting. But for this system to work, 2 critical conditions have to be met. First, the sweat has to reach your skin surface. Second, it has to evaporate into the surrounding air, and this is where fur becomes a catastrophic problem. Thick body hair creates what physiologists call a microclimate, a layer of air trapped close to your skin by the mat of fur. This layer is warm because it's heated by your body. It's humid because water vapor from your skin accumulates in it. And it's relatively still because the fur blocks airflow. When sweat evaporates into this microclimate, it doesn't cool you efficiently. The heat energy is released into the trapped air layer, which is already warm. The water vapor accumulates in the humid air, which slows down further evaporation. You end up with wet fur, which is actually worse than dry fur for thermoregulation. Wet fur conducts heat more effectively than dry fur, which means you lose heat faster when you're cold and gain it faster when you're hot. Wet fur is heavier, adding metabolic cost to any movement, and wet fur takes a long time to dry, creating extended periods of thermal discomfort. Animals with thick fur that need to cool down through sweating face, a fundamental engineering problem that evolution can't easily solve. Some, like horses, sweat. Anyway, despite the inefficiency, they produce massive amounts of lather, essentially overwhelming the problem through volume. But this is energetically expensive and requires constant access to water. Remove the fur, though, and everything changes. Sweat reaches bare skin. Airflow across that skin, whether from wind or from your own movement, carries away the evaporated moisture immediately. The cooling effect is dramatic, continuous, and precisely what our ancestors needed to survive their new lifestyle. But sweating creates its own problems. The biggest one is water loss. That 2 to 3 litres per hour of sweat we mentioned earlier, that has to be replaced. If it's not, you dehydrate rapidly, and dehydration is just as deadly as overheating, sometimes more so. This created a new evolutionary pressure. Our ancestors couldn't range far from water sources. They needed to know where every waterhole, stream and seasonal spring was located in their territory. They needed to develop water storage technologies, containers made from ostrich eggs, animal bladders, anything that could carry precious water during long hunts. They needed to cooperate, sharing knowledge about water sources, helping group members who were struggling with heat stress. The humans who survived weren't just the ones with the best sweating systems. They were the ones who were smart enough and social enough to manage the constant hydration challenge that came with those systems. And there's another component to human thermoregulation that's often overlooked. We breathe through our mouths when we run. Most mammals can't do this effectively. They're obligate nasal breathers during exertion, using their nasal passages to warm and humidify air before it reaches the lungs. But humans? We can switch to mouth breathing when we need to. This allows us to take bigger breaths, moving more air through our lungs, delivering more oxygen to working muscles. But it also helps with cooling. Air moving in and out through your mouth passes over moist mucous membranes. Some of that moisture evaporates, carrying away heat. It's a secondary cooling mechanism, less important than skin sweating, but still contributing to overall thermal regulation. And all of this, the eccrine sweat glands, the bare skin, the mouth breathing, it evolved together as a package. Each component reinforcing the others, creating a thermal management system that had never existed before in mammalian evolution. This system had another unexpected benefit. It helped solve one of the biggest challenges facing human evolution, the brain problem. Your brain is an energy hog, about 3 pounds of tissue consuming roughly 20% of your body's total energy budget. But energy consumption means heat production. Your brain generates about 15 watts of thermal energy continuously, 24 hours a day, just from thinking, remembering, processing sensory information. That might not sound like much, but it's equivalent to having a small light bulb burning inside your skull all the time. And brains are remarkably sensitive to temperature. Even a few degrees of overheating can cause serious damage. Most mammals keep their brain temperatures slightly lower than their core body temperature. They use specialized blood vessel structures in the nasal passages to cool blood before it reaches the brain. This works fine for brains that are using modest amounts of energy. But the human lineage was evolving larger and larger brains. More neurons, more connections, more metabolic activity, more heat. At some point, the standard mammalian brain cooling system wasn't going to be enough. The brain would overheat during the sustained physical activity that was becoming characteristic of human behavior. This would have created a hard limit on brain size. You can't evolve a bigger brain if doing so causes your ancestors to die from heat stroke every time they go hunting. The sweating revolution solved this. With efficient whole-body cooling, humans could maintain stable core temperatures even during intense physical activity. This meant the brain never experienced the dangerous temperature spikes that would occur in furred animals during similar exertion. The brain could grow larger, consume more energy, generate more heat. The body's cooling system could handle it because the cooling system wasn't limited to the nasal passages anymore. It was the entire skin surface, 2 square meters of evaporative cooling capacity. Some researchers think this created a positive feedback loop. Better body cooling allowed larger brains. Larger brains enabled more sophisticated hunting techniques, better tracking, improved tool use. More sophisticated hunting provided better nutrition, especially the high-quality protein from meat. Better nutrition supported even larger brains, and so on, spiraling upward toward the massive brains that characterize modern humans, all enabled by hairless skin and millions of sweat glands. But the sweating solution didn't just help with hunting and brain expansion. It gave human ancestors access to resources and environments that other predators couldn't efficiently exploit. The big cats hunted during dawn and dusk, ambush predators avoiding the heat of midday. Wild dogs hunted in coordinated sprints, but they too avoided the hottest hours. Humans? Humans could hunt in the middle of the day when every other predator was resting. They could pursue prey across open ground under full sun. They could quite literally run the biggest, fastest animals on Earth into the ground through the simple application of bare skin and sweat glands. This wasn't the only reason humans lost their fur. The other theories we'll explore, parasites, sexual selection, aquatic adaptations, they all probably contributed something. Evolution rarely has single causes when dealing with complex traits, but the thermoregulation revolution, this was transformative. This was the adaptation that let humans become pursuit predators despite being relatively slow and weak. This was what let human brains grow large without cooking inside their skulls. This was what forced human ancestors to develop sophisticated social systems for managing water resources. In short, this was one of the key innovations that made us human, and it only worked because we were willing to go naked into a world where every other mammal kept its fur coat on. The evidence is written across your skin right now. Those millions of sweat glands, invisible to the naked eye, working continuously to keep you cool. The bare skin that lets sweat evaporate efficiently. The dark pigmentation, if you're from equatorial populations, that protects that bare skin from ultraviolet damage. You're a sweating ape. A naked, sweating, running ape. And that combination of traits, unlikely as it seems, turned out to be one of the most successful evolutionary experiments in mammalian history. But sweating and thermoregulation aren't the only forces that shaped human hairlessness. There are other theories, other selective pressures, other ways that losing our fur might have provided advantages, and some of them are considerably stranger than anything we've discussed so far. There's a theory about human evolution that the scientific establishment absolutely hates, not just disagrees with, but actively despises. The kind of theory that can get you laughed out of academic conferences if you bring it up seriously. It's been called pseudoscience, speculative nonsense, and worse. And yet it keeps coming back, keeps attracting supporters, keeps asking questions that mainstream theories struggle to answer satisfactorily. It's called the Aquatic Ape Hypothesis. And while most anthropologists won't touch it with a 10-foot pole, some of the observations it makes about human hairlessness are genuinely puzzling. The basic idea goes like this. Sometime between 7 and 8 million years ago, our ancestors weren't living on the African savanna. They were living along coastlines in estuaries, spending significant time in shallow water, not as fully aquatic creatures like dolphins or seals, but as semi-aquatic primates who waded through tidal pools, foraged for shellfish, and used water as a refuge from predators. And during this aquatic phase, they lost their fur. The theory was first proposed by marine biologist Alistair Hardy in 1960, then developed extensively by writer Elaine Morgan starting in the 1970s. And from the moment it was published, the scientific establishment lined up to tear it apart. Paleoanthropologists called it speculative, unfalsifiable, based on superficial similarities rather than solid evidence. But here's the thing. Hardy and Morgan were asking legitimate questions. Questions that mainstream theories struggle to answer satisfactorily. Start with the most obvious one. Why are humans the only primates without fur? Every other ape, gorillas, chimps, orangutans, they're all covered in thick body hair, but humans are basically naked. Now, the Savannah Hypothesis says we lost our fur to stay cool while running in open grasslands. But plenty of savanna mammals have fur. Zebras, wildebeest, lions, they all manage just fine with full coats. So why did only humans need to become naked? The Aquatic Ape Theory offers a different answer. Look at aquatic mammals. Dolphins, whales, hippos, manatees. What do they all have in common? They're hairless or nearly hairless. Marine mammals lose their fur because it becomes a liability in water. Wet fur loses its insulating properties. It creates drag when swimming. It traps water against the skin, causing heat loss when you emerge from the water. Far better to lose the fur entirely and develop other adaptations like thick subcutaneous fat. And this is where the theory gets interesting. Because humans are weird among primates. We have a layer of fat directly beneath our skin that's far thicker than any other ape. Chimpanzees and gorillas are basically all muscle. Their skin sits right against their muscle tissue with minimal fat in between. But humans, even lean humans, have a significant layer of subcutaneous fat. Babies are born chubby, with fat, reserves that seem excessive for a terrestrial mammal. You know what other mammals have extensive subcutaneous fat? Aquatic ones, seals, whales, hippos. They use this fat layer for insulation in water where fur won't work. It provides buoyancy, helps with temperature regulation, and serves as an energy reserve during long periods of swimming or diving. Humans have exactly this adaptation, a layer of fat that seems designed for an aquatic lifestyle. Then there's breath control. Humans are the only primates who can consciously control their breathing. Chimps can't do it. Gorillas can't do it. Try to teach a chimpanzee to hold its breath or blow out a candle. It can't figure out what you want. But human babies can hold their breath underwater from birth. It's an instinctive response called the bradycardic reflex. You dunk a newborn in water, and they automatically seal their airways and stop breathing. This response is strongest in infants, exactly when it would be most useful if our ancestors were semi-aquatic. Adult humans can train themselves to hold their breath for minutes at a time. Free divers regularly go 4, 5, even 10 minutes without breathing. This isn't normal for a terrestrial mammal, but it's completely normal for semi-aquatic ones. Otters, seals, hippos, they all have sophisticated breath control that lets them forage underwater. Humans have this ability too, which seems strange if we evolved entirely on dry land. The theory goes further. Consider our body shape. Humans have relatively long legs compared to other apes. Our legs are built for forward motion, bipedal striding, but they're also pretty good for wading through shallow water. Stand a human, a chimp, and a gorilla in chest-deep water and watch what happens. The chimp and gorilla panic, struggling to keep their heads above water. The human instinctively stands upright, walks forward, uses the water to support their body weight. It feels natural because our proportions are adapted for it. Or look at our hands. Human hands have partially webbed fingers, not dramatically webbed like a duck's foot, but there's definitely a membrane connecting the base of each finger. Other apes don't have this. Their fingers are separate almost to the base. Why would humans have vestigial webbing if we'd never spent time in water? The theory even tries to explain human babies' relationship with water. Human infants are born helpless, unable to cling to their mothers the way other ape babies can. Put a newborn chimp on its mother's chest and it'll grab her fur and hold on. Put a newborn human on their mother's chest and they slide right off. We lack the gripping reflex that all other primates have. But human babies are natural swimmers. From birth, they can coordinate their limbs in a swimming motion, hold their breath underwater, and seem remarkably comfortable in aquatic environments. As if that's where we evolved to spend our earliest months, Morgan and Hardy even proposed specific geographic locations for this aquatic phase. They suggested the East African Rift Valley during periods when it was flooded by lakes and inland seas, or the shores of the Mediterranean where sea levels fluctuated dramatically, or coastal regions of Africa where early hominins might have exploited rich marine resources, places where our ancestors could have waded through shallow waters, diving for shellfish, catching fish in tidal pools, using the water as protection from terrestrial predators. The archaeological record does show that early humans exploited aquatic resources extensively. Shell middens, massive piles of discarded shellfish shells, appear at human sites going back hundreds of thousands of years. Coastal populations seem to have relied heavily on marine resources. Some researchers think the omega-3 fatty acids from seafood might have been crucial for brain development, providing the nutritional foundation for our large, metabolically expensive brains. But here's where the theory falls apart. Despite decades of searching, nobody's found the smoking gun. No fossils of semi-aquatic hominins with obvious aquatic adaptations. No skeletal features that clearly indicate diving or swimming. No deposits of human remains in ancient lake beds or coastal sites that would confirm prolonged aquatic living. The fossil record, sparse as it is, shows early humans in savanna environments, not aquatic ones. The mainstream scientific community has been brutal in its rejection of the aquatic ape theory. Paleoanthropologists point out that every supposed aquatic adaptation can be explained other ways. Hairlessness, for thermoregulation on open grasslands, subcutaneous fat, for energy storage during periods of food scarcity, breath control, as a byproduct of speech development, bipedalism, for efficient long-distance walking, not wading. Each individual piece of evidence crumbles under scrutiny. The theory also has a methodological problem. It cherry-picks similarities between humans and aquatic mammals while ignoring all the ways we're different. We don't have flippers. We don't have streamlined body shapes. We don't have the massive lung capacity of diving mammals. We don't have salt glands for excreting excess salt from seawater. We don't have any of the dozens of specific adaptations that true aquatic mammals possess. The similarities are superficial, the kind of convergent evolution you'd expect from any mammal that spent time in water, not evidence of a dedicated aquatic phase lasting millions of years. Most damningly, the theory requires a massive gap in the fossil record. If humans spent millions of years as semi-aquatic creatures, where are the transitional fossils? Where are the proto-humans with intermediate adaptations? The fossil record isn't complete, but it's not that incomplete. We've found fossils of early hominins in all sorts of environments. None of them show clear aquatic specializations. Yet the theory won't die. It keeps coming back, keeps attracting supporters, keeps generating debate. Why? Because it explains certain things so elegantly. The hairlessness, the fat, the breath control, the ease with which humans take to water. Babies who can swim before they can walk. Adults who can train themselves to free dive to extraordinary depths. Populations around the world who live almost amphibious lifestyles, spending hours each day in water. Maybe the truth is somewhere in the middle. Maybe our ancestors weren't fully aquatic, but they weren't fully terrestrial either. Maybe they were what ecologists call facultatively aquatic, creatures equally comfortable on land and in water, exploiting resources from both environments. Early humans living along lake shores and coastlines, wading through shallows to gather shellfish, diving for sea urchins, catching fish in tidal pools. Not spending enough time in water to become truly aquatic, but enough to lose their fur and develop some water-friendly adaptations. There's some genetic evidence for this compromise position. Studies of human populations that have lived by water for thousands of years show adaptations for diving and swimming. The Bachau people of Southeast Asia, who spend up to 5 hours a day underwater fishing, have evolved larger spleens that store oxygenated blood, allowing longer dive times. This suggests humans can adapt to aquatic lifestyles relatively quickly, and that such adaptations might have occurred repeatedly throughout our evolutionary history. So maybe the aquatic ape theory isn't entirely wrong. Maybe it's just overstated. Maybe our ancestors did spend significant time in and around water, enough to influence our evolution in subtle but important ways. Not enough to turn us into seals or dolphins, but enough to make us the only apes who can swim naturally, hold our breath consciously, and walk upright through chest-deep water without panic. The scientific community still rejects the theory in its strong form, but elements of it, the recognition that early humans exploited aquatic resources extensively, that water may have played a bigger role in our evolution than previously thought, these ideas are slowly being incorporated into mainstream thinking. Not as a replacement for the Savannah Hypothesis, but as a complement, a recognition that human evolution was complex, multifaceted, influenced by many environments and many selective pressures, because that's how evolution actually works, not through single dramatic adaptations, but through gradual accumulation of changes driven by complex environmental pressures. Maybe we didn't need to be fully aquatic to lose our fur. Maybe we just needed to spend enough time in water that hairlessness became advantageous. Combined with heat stress on savannas, combined with parasite pressure, combined with sexual selection, combined with a dozen other factors we haven't even considered yet. Human hairlessness probably doesn't have a single simple explanation. It's the product of multiple evolutionary pressures working together over millions of years. The aquatic ape theory, controversial as it is, reminds us to look beyond the obvious answers, to consider all the environments our ancestors inhabited, all the challenges they faced, because the truth is always more complicated than any single theory can capture. Now we need to talk about something unpleasant, something most people don't want to think about, especially when they're trying to fall asleep. But it's important, possibly more important than any other explanation for why we lost our fur. Parasites. Not the most romantic topic for a bedtime story, but stay with me here. Because what lives in fur might have been the real driving force behind human hairlessness. And the evidence is written in the DNA of creatures so small you'd need a microscope to see them, yet so deadly they've killed more humans than all the wars in history combined. Let's start with something simple. You're a human ancestor living 2 million years ago. You're covered in fur, just like your chimp relatives, and that fur is home to an entire ecosystem of creatures that see you as their personal planet. Lice crawling through the thick hair on your scalp and body, laying eggs that hatch into more lice. Ticks burrowing into your skin wherever the fur is thick enough to hide them from your picking fingers. Fleas jumping from individual to individual whenever your group huddles together for warmth. Mites living in hair follicles, feeding on oils and dead skin. And these aren't just annoying, they're deadly. Because here's the thing about fur-dwelling parasites. They don't just make you itch, they carry diseases. Typhus, spread by body lice, has killed millions throughout history. Plague, carried by fleas, has wiped out entire civilizations. Lyme disease, delivered by ticks, can damage your heart, your nervous system, your joints. In tropical environments where your ancestors lived, the parasite load on furred mammals is staggering. Modern primates in equatorial Africa can carry dozens of different parasite species simultaneously, each one draining energy, transmitting pathogens, reducing the host's ability to survive and reproduce. Let's be specific about what we're talking about here, because when we say parasites, we're not talking about abstract threats. We're talking about real organisms with real impacts on survival and health. Ticks. These arachnids are found in virtually every terrestrial ecosystem on Earth, but they're especially abundant in the transitional woodland savanna environments our ancestors were moving into. A single tick can transmit multiple diseases. Lyme disease, which can cause chronic neurological damage. Tick-borne encephalitis, which can be fatal. Anaplasmosis, ehrlichiosis, babesiosis. The list goes on. Modern studies of wild primates show that individuals can harbour hundreds of ticks at a time. They cluster in areas where the fur is thickest and hardest to groom, behind the ears, under the arms, in the groin region. Each tick feeds on blood for days or even weeks, slowly engorging itself while potentially transmitting pathogens with each meal. For a furred primate, ticks are nearly impossible to completely eliminate. You can groom your companions, pick off the ticks you can see and reach, but you'll never get them all. The tick population persists, generation after generation, a constant drain on health and energy. Lice. 3 species currently parasitize humans, and their evolutionary history tells us a fascinating story about when we lost our fur. Head lice, Pediculus humanus capitis, have been with us for millions of years. Their DNA shows they've been continuously evolving alongside human evolution since we split from chimpanzees. Body lice, Pediculus humanus, are different. They evolved from head lice relatively recently, somewhere between 83,000 and 170,000 years ago, and they're specifically adapted to live in clothing, not in body hair. Their existence proves that by that time humans were regularly wearing clothes and had already lost most of their body hair. Pubic lice, Thyrus pubis, have an even stranger story. Genetic analysis shows they're more closely related to gorilla lice than to human head or body lice. They apparently jumped from gorillas to humans around 3.3 million years ago. How this happened is unclear, possibly through butchering gorillas or using their nests for shelter, but the fact that they successfully colonized humans suggests we had already developed the thick pubic hair patch they needed to survive. Each louse species has its own impacts on health. Head lice cause itching and can lead to secondary infections from scratching. Body lice are vectors for serious diseases like epidemic typhus, which has killed millions throughout history. Trench fever, which devastated troops during World War I. Relapsing fever. Fleas. While humans today don't usually harbour fleas, our ancestors certainly did. Fleas thrive in the kind of communal sleeping arrangements early humans would have used. They jump easily from host to host, and they're vectors for plague, one of the deadliest diseases in human history. The Black Death, which killed 30 to 60% of Europe's population in the 14th century, was transmitted primarily by rat fleas. But human fleas, Pulex irritans, can also transmit plague, and they would have been common in the fur of our ancestors. Mites. These microscopic arachnids live in hair follicles and skin. Some species cause scabies, an intensely itchy skin condition. Others cause mange, which can lead to hair loss, open sores, and secondary infections. In furred mammals, mite populations can explode to enormous numbers. Each hair follicle becomes a potential home for multiple mites. The cumulative impact on health can be severe, particularly for young, old, or already stressed individuals. Now imagine you're a member of an early human group trying to transition from forest living to open savanna environments. You're spending more time in the sun. You're walking upright through tall grasses where ticks wait to drop onto passing animals. You're starting to live in larger social groups, sleeping close together, which means parasites can spread faster than ever before, and you're developing the cognitive capacity to notice patterns, to observe that some individuals seem healthier than others, that some people are constantly scratching, clearly infested, while others have clearer skin. The health impacts wouldn't have been subtle. Parasites cause anemia through blood loss. They suppress immune function. They transmit diseases that cause fevers, weakness, organ damage. An individual heavily infested with parasites would have been visibly less healthy, less energetic, less able to contribute to hunting and gathering, less attractive as a mate, and in the brutal calculus of natural selection, less likely to survive and reproduce. Consider the energetic costs alone. A heavy tick infestation can consume up to 5% of a mammal's daily blood production. That's blood that has to be constantly replaced, requiring energy and nutrients. Lice populations can number in the thousands on a single individual, each louse feeding multiple times per day. The itching and irritation cause sleep disruption. Constant scratching creates open wounds that can become infected. The immune response to parasites is energetically expensive, diverting resources away from growth, reproduction, and other vital functions. In marginal environments where food is scarce and energy budgets are tight, these parasitic drains could mean the difference between surviving a dry season and starving, between successfully raising offspring and watching them die from malnutrition or disease. Now imagine you're a member of an early human group trying to transition from forest living to open savanna environments. You're spending more time in the sun. You're walking upright through tall grasses where ticks wait to drop onto passing animals. You're starting to live in larger social groups, sleeping close together, which means parasites can spread faster than ever before. And you're developing the cognitive capacity to notice patterns, to observe that some individuals seem healthier than others, that some people are constantly scratching, clearly infested, while others have clearer skin. Natural selection is brutal in these situations. It doesn't care about your feelings or your comfort. It only cares about reproduction. And if parasites are reducing your health, making you weak, giving you fevers, covering you in sores, you're less likely to survive long enough to have children. Even if you do survive, you're less attractive as a potential mate. This is where the hygiene hypothesis gets interesting. Some anthropologists argue that the loss of body hair wasn't primarily about cooling or swimming. It was about creating an environment where parasites couldn't thrive. Think about the difference between a furred surface and bare skin. Fur provides insulation, darkness, humidity, countless hiding places. It's the perfect habitat for lice, which need to stay attached to hair shafts to survive. It's ideal for ticks, which can burrow deep and feed for days without being detected. It's heaven for fleas, which can lay eggs in the thick undergrowth and jump between hosts easily. Bare skin, by contrast, is a hostile environment for parasites. No place to hide, no hair shafts to grip. Any tick or louse on bare skin is immediately visible and vulnerable to being picked off. The sun directly hits the skin, creating temperatures too high for many parasites to survive. Rain washes away eggs and larvae that would otherwise be protected by fur. The selection pressure would have been intense. Individuals with less body hair would have lower parasite loads. They'd be healthier, more energetic, better able to hunt and gather. They'd have fewer disease outbreaks. Crucially, they'd be more attractive to potential mates, because visible health became easier to assess. This is sexual selection, at its most pragmatic. You're not looking for the most colourful plumage or the most elaborate display. You're looking for clear skin. Smooth, parasite-free skin that signals a healthy immune system and low disease risk. In environments where parasites are a major cause of death and disability, choosing a mate with visible evidence of parasite resistance could be the difference between your children surviving or dying young. The genetic evidence supports this timeline in fascinating ways. We know humans have 3 types of lice: head lice, which live in scalp hair; body lice, which live in clothing and only visit skin to feed; and pubic lice, which are actually more closely related to gorilla lice than to other human lice. The DNA of these lice species tells us when they diverged from each other, which gives us a timeline for when humans lost body hair and when we invented clothing. Body lice DNA suggests they split from head lice somewhere between 70,000 and 170,000 years ago. That's when body lice evolved to live in clothing rather than body hair, because there wasn't any body hair left to live in. This means humans had already lost most of their body hair by this point and had started wearing clothes regularly enough that lice could adapt to this new habitat. Head lice DNA is much older, suggesting they've been with us for millions of years, continuously living in our scalp hair. The fact that we kept head hair but lost body hair is actually strong evidence for the parasite hypothesis. Head hair could be groomed by other group members. Social grooming, where individuals pick through each other's hair removing parasites, is a major behavior in all primates. It's practical, it's bonding, and it works. But you can't effectively groom your own back, your own legs, your entire body surface. That fur was harboring parasites you couldn't reach. By losing body hair but keeping head hair, early humans created a situation where parasites were confined to a manageable area that could be systematically groomed, while eliminating the vast habitat that had existed across the rest of the body. It's actually an elegant compromise. Keep the benefits of hair, protection from sun on the head, possibly sexual signaling, while eliminating the massive parasite burden of full-body fur. The relationship between hair loss and group living intensifies this effect. As human populations began living in larger, more permanent groups, parasite transmission became a more serious problem. When you're a small band of 15 people moving frequently, parasites have limited opportunities to spread. But when you're a group of 50 or 100 people living in the same location for months, sleeping in close proximity, sharing food and tools, parasites can spread explosively. Modern studies of parasite loads in different mammal species show clear patterns. Species that live in large social groups and have thick fur suffer much higher parasite burdens than solitary species or hairless species. Bats living in caves with thousands of individuals are absolutely covered in parasites. Prairie dogs in large colonies have high tick and flea loads. Primates living in big troops show more parasite diversity and density than solitary primates. Humans were moving in the direction of larger groups, denser populations, more social complexity. Every step toward bigger communities increased the selective pressure against body hair. Every generation, the individuals with less hair were slightly healthier. Their children survived at slightly higher rates. Over hundreds of thousands of years, this cumulative pressure stripped away the fur that our ancestors had carried for millions of years. There's even evidence that hairlessness correlates with reduced disease transmission in modern contexts. Studies comparing infection rates between body regions show that hairy areas, armpits, groin, are more prone to bacterial and fungal infections than hairless areas. The warm, moist environment created by hair provides ideal conditions for pathogens. Historical records show that soldiers who shaved body hair in tropical environments had lower rates of certain diseases than those who didn't. Of course, losing hair created new problems. Without fur, humans became vulnerable to sunburn, heat loss at night, injuries from vegetation and insects. But these costs were apparently worth the benefits of reduced parasite load, and humans solved these new problems with technology. Clothing for warmth and protection, shelter for avoiding sun and rain, fire for warmth during cold nights, tools for processing food that might have become harder to eat without certain jaw adaptations. The parasite hypothesis also explains some puzzling details about human body hair distribution. We didn't lose all our hair. We kept significant hair in the armpits and groin, areas that coincidentally produce strong scent signals from apocrine glands. This suggests that hair in these regions might have been retained for social signaling, chemical communication that was important enough to outweigh the parasite costs. We also kept our eyelashes and eyebrows, which serve clear protective functions for our eyes. These hairs are coarse, regularly shed, and much less hospitable to parasites than the fine, dense body fur of our ancestors. They protect without harbouring the ecosystem of bugs that body fur supported. And we kept, as mentioned, our head hair, which could be long and thick. But head hair is unique. It's the one area of the body where other group members can effectively help with parasite control. Social grooming of head hair became a major bonding behaviour in human societies, something we still see echoes of in hairstyling, haircuts, and the intimacy of touching someone's hair. The timing of hair loss, probably between 1 and 2 million years ago based on genetic evidence from skin pigmentation genes, coincides with other major transitions in human evolution. This is when brain size is increasing rapidly, when tool use is becoming sophisticated, when group sizes are growing, when humans are spreading into new environments with different parasite pressures. It's possible, maybe even likely, that hair loss was part of a package of adaptations that all reinforced each other. Bigger brains needed better cooling, which hairlessness provided. Larger groups needed better parasite control, which hairlessness enabled. More sophisticated social structures benefited from visible health signals, which bare skin revealed. Better tool use allowed clothing manufacture, which compensated for the loss of fur's protective functions. None of these factors alone might have been enough to drive the evolution of hairlessness. But together, they created a situation where losing fur provided multiple simultaneous advantages. Parasites might not have been the only reason we lost our hair, but they were probably a major part of the equation, a constant deadly evolutionary pressure that shaped our bodies in ways we're still living with today. Every time you look at your smooth arm or leg, you're seeing the result of millions of years of warfare against creatures so small you can barely see them. Creatures that once called your ancestors' fur home. Creatures that our lineage eventually evicted by burning down the house, metaphorically speaking. And the victory wasn't complete. We still have parasites. Head lice still infest millions of people worldwide. But the parasite load on modern humans is dramatically lower than what our furred ancestors would have experienced. That reduction in parasites, that improvement in health and survival, that might have been the tipping point. The factor that made hairlessness worth all the other vulnerabilities it created. Because in the end, evolution doesn't optimize for comfort or convenience. It optimizes for survival and reproduction. And if losing your fur meant losing the deadly parasites that lived in it, the trade-off was worth making. Even if it meant spending the rest of human history trying to compensate for that, loss with clothing and shelter and fire. So we've talked about why humans might have lost their fur, the heat of the savannah, the demands of persistence hunting, the possibility of aquatic living, the pressure from parasites, all of these environmental factors creating selection pressures that favoured hairlessness. But here's what really matters. Here's what makes this more than just theoretical speculation. We can actually see the genetic changes that made us naked. Scientists have identified the specific DNA mutations that transformed us from furry apes into hairless humans, and those mutations tell a story. Let's start with the basics. Hair growth is controlled by a complex network of genes, dozens of them, all working together in carefully orchestrated patterns. But a few key players do most of the heavy lifting. The gene HR, which stands for hairless, controls the transition between different phases of hair growth. When HR is working normally, it keeps hair follicles cycling through growth and rest phases, producing the thick terminal hairs that cover most mammals. But in humans, something changed. Comparative genomic studies, where scientists line up the DNA of different species and look for differences, have found several mutations in the human version of HR. These mutations don't eliminate the gene entirely. That would be lethal, causing severe developmental problems. Instead, they modify how the gene functions, reducing its activity in most parts of the body. The result? Hair follicles that produce vellus hairs instead of terminal hairs. The thin, fine, almost invisible hairs that cover most of your body. The evolutionary compromise between being completely bald and being fully furred. But HR isn't working alone. Another crucial gene is FGF5, fibroblast growth factor 5. This gene determines how long hair can grow before the follicle enters its resting phase. In mice with broken FGF5 genes, hair just keeps growing and growing, creating these weird long-haired mutants that look like tiny Afghan hounds. In humans, FGF5 works normally in certain areas, like your scalp, which is why hair on your head can grow several feet long if you never cut it. But in other areas, the gene has been modified, or its expression has been reduced, limiting hair length to barely visible fuzz. Then there's EDAR, a gene that controls the density and thickness of hair follicles. Different versions of this gene create different hair textures across human populations. East Asians, for instance, tend to have a specific variant of EDAR that produces thicker individual hairs but fewer total follicles. This variant arose fairly recently in evolutionary terms, probably within the last 30,000 years, showing that human hairlessness is still evolving, still being refined by natural selection. What's fascinating is that when scientists use molecular clock analysis, looking at how many mutations have accumulated and calculating backward to estimate when changes occurred, they get a timeline that matches perfectly with the other evidence for human hair loss. The key mutations in HR appear to have become widespread around 1.2 million years ago, give or take a few 100,000 years, which in evolutionary terms is pretty precise. This is right around the time the fossil record suggests our ancestors were losing their fur, right around the time the climate was forcing populations into situations where hairlessness would be advantageous. But losing hair created an immediate problem, a deadly serious problem. Without fur, human skin was suddenly exposed to something it had never dealt with before: direct sunlight, intense, unfiltered ultraviolet radiation that could cause sunburn, skin cancer, and destroy folate, a crucial vitamin needed for DNA synthesis and fetal development. The solution came through another set of genetic changes, mutations in genes that control skin pigmentation. The key gene here is MC1R, melanocortin 1 receptor. This gene determines how much melanin, dark protective pigment, your skin cells produce. In our furry ancestors, MC1R didn't need to be particularly active. The fur provided protection from UV radiation, so skin color didn't matter much. You could have pale skin under dark fur and survive just fine. But once the fur was gone, pale skin in equatorial Africa became a death sentence. Severe sunburn, yes, but more importantly, UV radiation breaks down folate in the bloodstream. Low folate levels cause neural tube defects in developing fetuses, leading to miscarriages and birth defects. Any individual with a pale skin mutation would have lower reproductive success. Their babies would be less likely to survive. So natural selection acted fast. Within probably just a few thousand generations, the human populations remaining in Africa had evolved very dark skin. Not just a tan, actual genetic changes that made their skin cells produce massive amounts of melanin. The MC1R gene in African populations shows evidence of strong positive selection, meaning individuals with dark skin variants were significantly more likely to survive and reproduce than those without. But here's where the story gets complicated. Because modern human populations show tremendous variation in skin color, from the darkest possible shades in parts of Africa and Melanesia to the palest complexions in Northern Europe. This variation tells us something important. The evolution of hairlessness and the evolution of skin color happened in stages, not all at once. When our ancestors first lost their fur in Africa, they evolved dark skin as protection. But as human populations later migrated out of Africa into Europe and Asia, they encountered environments with much less intense sunlight. Suddenly, dark skin became a disadvantage. You need some UV radiation to hit your skin to produce vitamin D. Without enough vitamin D, you get rickets, bone deformities, problems with calcium metabolism. In the low-light conditions of Northern Europe and Northern Asia, especially during long winters, dark skin blocked too much UV radiation. People couldn't produce enough vitamin D, so populations that migrated north evolved lighter skin. The MC1R gene shows different mutations in European populations compared to African ones, mutations that reduce melanin production. Interestingly, East Asian populations evolved light skin through different genetic changes, mutations in different genes entirely. This is convergent evolution. Multiple populations independently solving the same problem through different genetic routes. It suggests that the selection pressure for appropriate skin color in different environments was incredibly strong. Strong enough to drive rapid evolution in multiple populations simultaneously. The molecular clock data suggests these skin color adaptations happened fairly recently. The variants associated with pale skin in Europeans probably emerged within the last 30,000 to 50,000 years. Some researchers think it might have happened even more recently, possibly as late as 10,000 years ago, accelerated by the adoption of agriculture, which provided a diet lower in vitamin D than the hunting and gathering lifestyle. But we're getting ahead of ourselves. The key point is that losing hair required a cascade of genetic changes. First, mutations that reduced hair growth. Then, mutations that adjusted skin pigmentation to match local UV radiation levels, and the genetic changes didn't stop there. Remember how humans retain terminal hair in certain areas? Your scalp, armpits, groin, and for men, facial hair and chest hair. Why? What makes these areas special? The answer lies in gene expression patterns. The genes for hair growth are still present everywhere in your body. Every skin cell has the complete instruction manual, but different genes get turned on and off in different locations, controlled by regulatory sequences that act like molecular switches. In areas where humans retain thick hair, those regulatory switches kept the hair growth genes fully active. On your scalp, this probably relates to thermoregulation, protecting your brain from overheating and preventing heat loss in cold conditions. In your armpits and groin, the retained hair serves a different function. These areas contain specialized sweat glands, apocrine glands that produce the thicker, odor-causing secretions involved in scent signaling. The hair in these regions helps disperse those scents, broadcasting chemical signals about your age, sex, and reproductive status. The genetic changes that made humans mostly hairless apparently left these regions alone, possibly because the social signaling functions were important enough that natural selection preserved them. Facial hair in men is particularly interesting because it's controlled by sex hormones, specifically testosterone. The genes are the same in men and women, but testosterone activates additional regulatory switches during puberty in males, causing thicker, darker hair growth on the face, chest, and other areas. This suggests that facial hair evolved as a sexually selected trait, possibly as a signal of male maturity and dominance. The genetic basis for this involves androgen receptor genes that respond to testosterone by activating hair growth programs in specific regions. Modern human populations show significant variation in body hair, and that variation is genetically determined. Some populations are relatively hairy, others quite smooth. Mediterranean populations, for instance, tend to have more body hair than East Asian populations. This reflects different selection pressures and different evolutionary histories. In colder climates where humans wore more clothing, there might have been reduced selection pressure for complete hairlessness, allowing some populations to retain more body hair. In hotter climates, the advantages of efficient sweating might have driven more complete hair loss. What's really remarkable is how fast all these changes happened. From the first mutations in hair growth genes around 1.2 million years ago, to the diversification of skin color and body hair patterns in different populations over the last 100,000 years. Human hairlessness evolved in what amounts to an evolutionary eye blink. This tells us that the selection pressures must have been enormous. Individuals with the right mutations for their environment had significantly better survival and reproductive success than those without. Natural selection was operating at maximum intensity, rapidly reshaping the human body to meet new challenges. And we can see this rapid evolution in our genomes today. When geneticists look at the patterns of variation in hair and skin pigmentation genes, they find signatures of recent selection. Long stretches of DNA with very little variation, indicating that particular gene variants swept through populations so fast that neighboring DNA sequences got carried along unchanged. This is the genetic fingerprint of evolution in action, proof that human hairlessness wasn't some gradual drift, but an active response to intense environmental pressures. The story written in our DNA is clear. Our ancestors lost their fur through specific, identifiable genetic changes. Those changes created new vulnerabilities that required additional adaptations, and the entire process was shaped by natural selection, operating across hundreds of thousands of years and millions of individual lives. Every human alive today carries these mutations, these evolutionary scars from our species' long journey from furry ape to naked ape. We are, quite literally, the descendants of the ones who survived being naked when being naked was dangerous. But genetic changes alone don't tell the whole story. Because losing our fur had consequences that went far beyond just genetics. It changed how we lived, where we could live, and what we needed to do to survive. Consequences that would ultimately shape everything about being human. Here's what most people don't realize about losing our fur. It wasn't just a cosmetic change. It fundamentally transformed what it meant to be human. Because once your ancestors shed that protective coat of hair, they became vulnerable in ways no other primate had ever experienced. And vulnerability, it turns out, is one hell of a catalyst for innovation. Think about it. A chimpanzee can sleep under a tree when it rains and wake up uncomfortable but alive. Try that as a naked human in a temperate climate and you're looking at hypothermia by morning. A gorilla can trek through thorny undergrowth without a second thought. You, with your exposed skin, would be torn to ribbons within minutes. Other primates can handle temperature swings of 30 or 40 degrees without much difficulty. You need shelter, fire, and clothing just to survive a typical spring day in most of Europe or Asia. So here's the question. If being naked made us so vulnerable, How did we become the most successful large mammal on the planet? How did these hairless, fragile creatures not just survive but dominate every terrestrial ecosystem from the Arctic to the Sahara? The answer is that our nakedness forced us to become inventors, not just tool users. Lots of animals use tools, but systematic, creative, problem-solving inventors who could adapt to any environment through technology and culture, rather than waiting millions of years for biological evolution to do the work. Let's start with clothing, because that's the first and most obvious consequence of hairlessness. Lose your fur coat, and you need a replacement. The archaeological evidence for early clothing is frustratingly sparse, because organic materials like leather and plant fibers don't preserve well. But we can date the invention of clothing through a surprising source: lice. There are 3 types of lice that parasitize humans: head lice, which live in scalp hair, pubic lice, which live in coarser body hair, and body lice, which live in clothing. Genetic analysis of body lice shows they diverge from head lice somewhere between 83,000 and 170,000 years ago. That's when body lice evolved as a distinct species, and they could only do that once humans started wearing clothing regularly enough for the lice to specialize in that ecological niche. So by around 100,000 years ago, your ancestors were wearing clothes. Not occasionally, not just for special occasions, but regularly enough that parasites evolved to exploit this new habitat. This represents a cognitive revolution. Making clothing isn't like picking up a stick to probe for termites. You have to imagine the finished product before you start. You have to understand abstract concepts like cutting, joining, and fitting. You need to develop entirely new technologies: scraping hides, processing plant fibers, creating needles and thread, inventing ways to tie or stitch materials together. More importantly, you have to teach these skills to your children. Clothing manufacture became one of the first truly complex technologies that required generational knowledge transfer. A young chimpanzee can learn to use a termite stick by watching Mum a few times. Learning to make a fitted garment from animal hides requires years of instruction and practice. This created selection pressure for teaching ability and learning capacity. Individuals who were better at acquiring and transmitting complex skills had survival advantages. Their children were more likely to survive cold nights. Their groups were more likely to thrive in challenging environments. Over thousands of generations, this refined human, cognitive abilities in ways that set us apart from every other species. But clothing was just the beginning. Because here's the thing about being a naked ape in a world that regularly drops below freezing. Clothing helps, but it's not enough. You need fire. Not just for cooking, lots of animals can eat raw food. Not just for protection, though that's useful. You need fire to literally stay alive through the night in most of the world's temperate and cold zones. Early humans had been using fire opportunistically for maybe 1 million years. Lightning strikes, natural wildfires, these could be exploited for warmth and cooking. But hairlessness created pressure to control fire systematically. To make it on demand, maintain it through wet conditions, transport it from place to place, and teach others how to manage it safely. Archaeological sites from around 400,000 years ago show evidence of systematic fire use. Hearths that were maintained over long periods, careful placement of fires inside caves and rock shelters, strategic use of different woods for different purposes. This represents another technological leap. Fire management requires planning, knowledge of materials, understanding of combustion and airflow. It's chemistry and engineering without the formal concepts. More than that, fire created new social dynamics. A fire needs tending. Someone has to gather fuel, maintain the flames, make sure it doesn't spread dangerously. This creates opportunities for labour specialisation. While some group members hunt or gather, others maintain the fire. While some sleep, others keep watch and feed the flames. Fire also changed when and where humans could socialise. Before controlled fire, your ancestors would have been like other primates, active during daylight, resting at night in trees or protected locations. Fire extended the day. It created a focal point for evening gatherings. Anthropologists think this is when storytelling evolved, when elder knowledge began to be systematically transmitted through narratives told around the fire. The technology that we needed because we lost our fur became the centerpiece of human cultural evolution. And then there's shelter. Third animals can sleep rough most nights without serious consequences. Naked humans cannot. We need protection from elements that other primates shrug off. This forced our ancestors to become builders and architects. Early shelters were probably simple, caves and rock overhangs, natural protection that required minimal modification. But caves aren't everywhere, and they're often occupied by other large predators who aren't interested in sharing. So humans learned to build. The earliest constructed shelters date back at least 400,000 years. Circles of stones that probably anchored wooden frames covered with hides or vegetation. These aren't impressive by modern standards, but they represent something revolutionary. The ability to create artificial environments, to modify your surroundings rather than just adapting to them. This skill set would eventually let humans colonize literally every land environment on Earth. The Arctic, where winter temperatures drop to -40 and darkness lasts for months. The tropical rainforests where constant moisture and biting insects make life miserable for any large mammal. The deserts where daytime heat can kill in hours and nights get cold enough to freeze. No other large mammal lives in all these environments. Polar bears stay in the Arctic, jaguars stick to the tropics, camels avoid the poles. But humans, fragile, hairless, vulnerable humans, we're everywhere. Not because we biologically adapted to each environment, that would take millions of years, but because we culturally adapted. We invented parkas and igloos for the Arctic, breathable clothing and raised dwellings for the tropics, desert robes and water storage for arid regions. Our nakedness, which should have been a fatal weakness, became our greatest strength because it forced us to develop the cognitive and cultural tools to adapt to anything. But the consequences went beyond just technology. Hairlessness changed our social dynamics in profound ways. Because when you're naked, you're visible. Every scar tells a story. Every injury is apparent. Physical condition, age, health status, these become immediately obvious in ways they aren't for furred animals. This created new opportunities for social signaling. Body decoration emerged as a way to communicate identity and status. Ochre and other pigments show up in archaeological sites from at least 100,000 years ago. Not for camouflage or practical purposes, but for adornment. Humans were painting themselves, creating visual markers of group membership, individual identity and social status. The same is true for scarification and tattooing, which show up in the archaeological record through preserved skin and artistic representations. These aren't just decorations, they're information systems, ways of encoding social meaning onto the visible canvas of naked skin. Modern humans continue this tradition in wildly diverse ways. Every culture has developed elaborate practices around body hair maintenance. Some remove it almost entirely, others cultivate specific styles. Some see hairlessness as attractive, others view it as childish or weak. There's no universal standard because the meanings we assign to body hair are entirely cultural, not biological. What's fascinating is that humans are the only species that deliberately modifies its hair for social and aesthetic reasons. No other animal spends time styling, cutting, dyeing, or removing its fur. This behavior only makes sense in a species that's already mostly hairless, where the remaining hair has become a canvas for cultural expression rather than serving primarily functional purposes. And we're not done evolving. Evolutionary biologists who study human morphology have some interesting predictions about where we're heading. Because here's the thing about body hair, we're still losing it. Modern humans have less body hair than humans did 10,000 years ago. And that trend seems likely to continue. Why? Because we've created artificial environments, climate-controlled buildings, protective clothing, central heating and air conditioning. Natural selection for body hair has essentially stopped in modern technological societies. There's no survival advantage to having more body hair when you live in a house and wear clothes. There's also no significant disadvantage to having less. So what happens is genetic drift. Random mutations that reduce body hair don't get selected out because they don't affect survival or reproduction. Over thousands of generations, these mutations accumulate. Some models suggest that in another 100,000 years, humans might have even less body hair than we do now. Perhaps retaining only eyebrows, eyelashes, and scalp hair, which still serve clear protective functions. But here's what's truly remarkable. None of this matters for human survival anymore. Whether we have more body hair or less, whether we keep our remaining hair or lose it entirely, it won't affect our ability to thrive on this planet. Because we long ago transcended the biological constraints that limit other species. We lost our fur and had to invent clothing that made us inventors. We needed fire and had to control it that made us engineers. We required shelter and had to build it that made us architects. Every vulnerability that came from our nakedness forced us to develop new capabilities, new technologies, new social systems, new ways of understanding and manipulating the world around us. And that's the real consequence of hairlessness. It didn't just change what we looked like, it changed what we were capable of becoming. It transformed us from just another African ape into something unprecedented. A species that could adapt to any environment, not through evolution, but through innovation. A species that could colonize an entire planet not by developing specialized biology for each habitat, but by developing the cognitive tools to create specialized solutions for each challenge. We are naked because our ancestors needed to run down prey under the African sun, or because they spent time in the water, or because they needed to avoid parasites, or because sexual selection favored it. Probably all of these reasons played some role, but we are human, truly human, because being naked forced us to become something more than our biology. Something that could survive through creativity rather than adaptation, through culture rather than evolution, through innovation rather than instinct. That's the legacy of hairlessness. Not just the strange appearance it gives us, but the extraordinary capabilities it forced us to develop. So here's where we end up after following the trail of our missing fur across millions of years of evolutionary history. With a simple but profound realization, there was no single moment when humans lost their hair, no dramatic mutation, no sudden evolutionary leap, just layer upon layer of evolutionary pressures, each one pushing our ancestors toward increasingly bare skin, the Savannah Hypothesis, running under the brutal African sun, needing to dump heat faster than any other mammal, the ability to pursue prey for hours in conditions that would kill furred animals through overheating, the aquatic influences, maybe spending enough time in water that fur became a liability rather than an asset, wading through shallows, diving for shellfish, using water as refuge and resource. The parasite problem, every louse, every tick, every disease-carrying insect providing natural selection with another reason to favour hairless individuals. Bare skin creating a hostile environment for the creatures that had made fur their home for millions of years. Sexual selection. Smooth skin becoming a signal of health, youth, attractiveness. The ability to assess a potential mate's condition at a glance, no fur hiding infections or infestations. Social signalling. The ability to blush, to show emotion through our exposed faces, creating deeper bonds and more sophisticated communication than any furred primate could achieve. None of these explanations alone is sufficient, but together they paint a picture of evolutionary forces converging on the same solution. Hair had to go, and when it did, everything changed. Because here's the thing about losing our fur, it wasn't just a cosmetic change. It was a cascade that shaped nearly everything that makes us human. Without hair, we needed clothing. The development of clothing required planning, tool-making, abstract reasoning. It pushed our ancestors to think ahead, to prepare for future needs. Without fur's protection, we needed shelter. Not just temporary sleeping spots, but constructed spaces that required cooperation and innovation to build. Without hair to provide insulation, we needed fire. Mastering fire meant mastering one of nature's most dangerous forces. It meant developing the cognitive capacity to maintain and control something that could easily kill you. The thermoregulation problem forced us to become the planet's best endurance athletes. That shaped our entire body plan: long legs, narrow hips, specialized foot architecture. The need to cool our overheating brains during persistence hunts drove selection for more efficient neural structures. Bigger brains, yes, but also better organized, more energy efficient, and the social aspects of hairlessness. The ability to read emotions on bare faces, to signal through blushing and complexion changes. That laid groundwork for the sophisticated social systems that would eventually let us build civilizations. We are naked apes. And that nakedness connects to language, tool use, art, culture, everything that separates us from our closest primate relatives. All of it traces back, at least in part, to those first ancestors who started losing their fur under the African sun millions of years ago. The ones who discovered that bare skin could be an advantage if you were smart enough and social enough to work around its vulnerabilities. Who turned a potential weakness into humanity's greatest strength. Who learned to dominate every environment on Earth despite having none of the natural armor, fur, claws, or fangs that other apex predators relied on. They did it with intelligence, cooperation, and the evolutionary adaptations that came from being furless primates trying to survive in a dangerous world. Every time you sweat through a workout, you're using the cooling system that hair loss made possible. Every time you bundle up against the cold, you're compensating for the insulation your ancestors lost. Every time you read emotion on someone's face, you're using the communication advantages that bare skin provided. We are the descendants of the naked apes, and that nakedness made us human. Your ancestors were those individuals, the ones who survived despite being naked and vulnerable, who turned their lack of fur into an evolutionary advantage by becoming smarter, more innovative, more adaptable than any furred creature could be. The genetic evidence is written in your DNA. The mutations in HR and FGF5 and EDAR that control hair growth, the changes in MC1R that gave different populations their skin colours, all of it carried forward from ancestors who lived and died millions of years before you were born. The anatomical evidence is written in your body. The millions of eccrine sweat glands covering your skin, the strategic patches of hair retained on your head, in your armpits and groin, the darkly pigmented skin of equatorial populations or the pale skin of northern peoples, each adapted to local UV radiation levels. The behavioural evidence is written in your culture. The clothes you wear, descended from the first hides and plant fibres our ancestors wrapped themselves in 100,000 years ago. The shelter you sleep in evolved from the first constructed dwellings built 400,000 years ago. The fire you control, whether it's a campfire or a gas stove, carrying forward the mastery of flame that became essential when we lost our natural insulation. Even the social behaviours, the way you style your hair, paint your face, decorate your body. All of it descended from the first humans who realised that bare skin could be a canvas for identity and status. The timeline is clear now. 6 million years ago, our ancestors were fully furred, just like modern chimpanzees, living in forests, moving through trees covered in protective hair. 4 million years ago, early bipedal hominins like Australopithecus were probably still mostly furred, though they were spending more time on the ground, walking upright, more consistently. 2 million years ago, with the emergence of early Homo species, the transformation began in earnest. Body proportions changing, becoming taller and more linear. Hair thinning, sweat glands proliferating. The shift from furred ape to naked ape happening gradually but inexorably. 1.2 million years ago, dark skin emerging as protection once the fur was gone. The mutations in MC1R spreading through African populations, providing the melanin shield that naked skin required. 700,000 years ago, by the time of Homo heidelbergensis, our ancestors were probably mostly hairless, retaining strategic patches but losing the dense body fur that had characterized primates for millions of years. 100,000 years ago, clothing becoming regular enough that body lice evolved to exploit this new habitat. Fire use becoming systematic, shelter construction becoming sophisticated, and from then until now, humans spreading across the planet, adapting not through biological evolution, but through cultural innovation, creating technologies to survive in every environment, from Arctic tundra to tropical rainforest to desert to high altitude, all enabled by the nakedness that forced us to become inventors. The story of human hair loss is really the story of human exceptionalism. Not because we're better than other animals in some cosmic sense, but because we found a unique evolutionary path. Most species adapt to their environment slowly, over millions of years, through genetic changes. Humans learn to adapt quickly, within generations, through cultural and technological changes. Most species are limited to specific habitats, specific ecological niches. Humans can live anywhere we choose because we create our own habitats. Most species are constrained by their biology. Humans transcended those constraints by losing the one thing that seemed most essential, our protective coat of fur, and then inventing everything we needed to compensate for that loss. If you're still awake, if this journey through evolutionary history has given you a new appreciation for your own naked skin, let me know in the comments where you're listening from. Tokyo at dawn, Seattle at midnight, somewhere in between, all of us descendants of the naked apes, carrying forward the legacy of that ancient transformation. Because understanding our past, understanding why we look the way we do and how we got here, that's not just academic curiosity, that's understanding ourselves. The naked truth about human evolution is that we're all carrying the legacy of every evolutionary pressure, every environmental challenge, every genetic quirk that shaped our ancestors over millions of years. And somehow, against all odds, they survived long enough to become us. Hairless, vulnerable, dependent on technology and culture for survival. But also intelligent, adaptable, capable of thriving in environments our furred ancestors could never have imagined. We lost our fur and gained the world. The technologies, the social structures, the cognitive abilities that make us human, all of it emerged from the necessity created by our nakedness. All of it built on the foundation of bare skin and sweat glands, and the vulnerabilities that forced us to become more than our biology. So sleep well, if that's where you're headed. Dream of ancient savannas and persistence hunts, of ancestors running under the hot sun, their bare skin glistening with sweat, chasing prey to exhaustion through sheer endurance. Dream of the first fires, carefully tended through cold nights, of the first shelters, crude but effective, of the first clothing, animal hides wrapped and tied, providing the protection that fur once gave. Dream of the long journey from furred ape to naked ape to technological being, the millions of years of evolution that made you possible, and remember that every breath you take, every drop of sweat you produce, every cognitive leap you make connects back to those ancestors who lost their fur and had to reinvent what it meant to be a primate. They succeeded. You're the proof. The mystery of why humans lost their fur isn't really a mystery anymore. It's a story. A complex, multifaceted story with no single answer but dozens of contributing factors. Heat stress and persistence hunting, aquatic resources and parasite pressure, sexual selection and social signaling, genetic mutations and environmental change, all of it working together over millions of years to create something unique. A hairless, sweating, running, thinking ape that could adapt to anything. That's us. That's our inheritance. That's the legacy of the naked ape, and it's written on every inch of your skin.